Hi everyone, and welcome to our ninth lecture of CSC 110. In this lecture, we're going to be studying the internet. Okay, and I think everyone would agree that the internet is a very important part of computer technology today. And if it weren't for the internet, computers really would not be the things that they are now. We call them computers, which comes from the word to compute, like to calculate something, but really they're more like communicators because what the internet has allowed us to do is to share information very quickly. Okay, and that's a good thing, but it's also a bad thing. And so a lot of what this lecture is going to be is about how to protect yourself on the internet, in the sense of knowing where your information goes and what sorts of things to watch out for to make sure that your information is going into the right place and not the wrong place. Okay, this is not too hard to do. The internet started off as just it was actually a DARPA project. That's a project by the U.S. military, and when it first started, it really didn't take into consideration anything about security or anonymity. Okay, and so people that use the internet, they didn't care that if other people saw their information. But today, that's a big issue because the internet, especially since like the mid 90s or so, early 2000s, has been used for business. And the last thing you want is for your information to get into the wrong hands. Okay. Now, like I said, a lot of this technology has been built up over time so that when you use the internet, you automatically get that security. But, you really want to know what's going on in case there's some certain warning signs that that security isn't there. And so I'm going to show you how the internet works, not in hopefully too much detail, but just enough detail so you have an idea of how it's working, where your information is going, and how you know that it's being protected. Okay, and there's actually two levels to internet insecurity. One of them is just security, making sure that your information doesn't fall into the wrong hands. But the other one is anonymity, and that is, is it possible to surf the internet while hiding your identity? Okay, you can transmit information securely so that a third person can't see the information, but can you surf the internet anonymously so that people can't see who you are when you surf the internet or use the internet in any way whatsoever? And so we're going to look at that. All right, and that's one aspect of this lecture. Another aspect of this lecture is that the internet has allowed for new technologies to emerge, and this is going to be our last topic, and it has to do with peer-to-peer networks. These are networks which are diffuse. They're distributed in a way that has no center. Okay, and this has allowed for a whole new type of set of technologies that we don't quite have anything like that in the real world. Okay, so one of the things that this is allowed for is actually a new type of currency like bitcoins. Okay, and once upon a time, I used to teach about bitcoins even 10 years ago, and people were like, well, what is this thing? And I think pretty much everyone today knows what bitcoins are because they're revolutionizing the money world. Okay, don't think of bitcoins as just a digital currency. Like US dollars are digital. When you go and buy stuff, at the store, a lot of people will just use your credit card or debit card. You won't even pull out cash or paper cash. Okay, you'll just use a card. That's digital money. But the bitcoins are not just digital; they're cryptocurrency, which is a totally different type of currency. That it's another way that currency works. Okay, rather than dollars, which are a fiat currency. Okay, and because of this, it's kind of revolutionized the way money works. All right, and so it's good to know these things. You're going to wonder, why am I getting so technical with this stuff? I'm trying actually to stay as untechnical as possible, as simple as possible, but to really have to walk away from this course and really have an appreciation of what's happening on the internet, you do have to dive a little bit into the details. Okay, hopefully not too much though. Okay, but just enough so that for years to come, you'll have a good understanding of what's happening to your information when you pick up your phone and you're surfing the net or doing whatever, or even sending a text message. Okay, so let's start. The first thing you need to know about are LANs and routers, and what's that? Okay, so basically the way you can picture the entire internet, like the whole thing, the whole entire global interconnection through the internet, is in terms of what are called LANs, which are local area networks. These are small local networks that they're just like in your home or like a classroom, or like the dorms if you're living in the dorms, or something like that. Okay, so generally they're the size of one building, and these are called local area networks. Okay, and computers there communicate with one another directly. They don't go through any kind of intermediate path. Okay. But these local area networks, if that's all you had, they would just form this patchwork and they wouldn't be connected to one another. So, you might have like one house with a LAN and another house with a LAN. And if those two LANs were not connected, then how would they communicate to one another? And so not only is the internet made up of this patchwork of LANs, okay, again, local area networks, LANs, but there's also something that glues the LANs together. And these are routers, okay? And to route means to, just direct traffic, okay? Like, you're routing traffic one way or another way, okay? And sometimes they're called routers, but here in the US we tend to call them routers, okay? And what these routers are, they're just devices, small little boxes, and I'll show you what they look like in a minute. And these routers, what they do is they'll take the information from one LAN, and not all the information, but if that information is not destined for another computer in the same LAN, then it gets passed by the router to another LAN. Okay, and so the routers will connect two LANs. All right, but it's a little bit more than that, because if all you had were just two LANs, then that would be pretty boring. It wouldn't, connect the entire world. The LANs are all connected to one another by routers, and these routers, they know about one another because they talk to one another, and they say something like, I'm connected to this other router over here. And another router will say, oh, that's nice, I'm connected to this router. And so they know kind of like how the whole world is connected. And even if you add and remove routers, they learn from one another what their connectivity is, like how they're connected to one another. And so generally speaking, when you send a packet out on the internet, I'll tell you what a packet is in a minute, but when you send information out on the internet, they pass through about 10 routers or so before they get to where they're heading. Okay, before they get to where they're heading. And so these routers, that your LAN has a router, and it'll pass it to the next router, it'll pass it to the next router, it'll pass it to the next router, and eventually it'll get to its destination. And then that final destination will pass the information back. Okay, and so that's generally speaking how the internet works. All right, in terms of LANs and routers. All right, now, like I said, the whole world's been connected through these routers. And if you go to the Wikipedia page just on internet, so this is like wikipedia.org/internet, you'll see this picture that I'm going to show you right now. Okay, and this picture is supposed to be a realistic picture of what the entire internet, the connectivity of the entire internet is. Okay, and I'll just zoom in a little bit there like that, and it's kind of a I don't know, it's not that useful a picture. It is supposed to be a realistic picture that things are connected this way. But what you're supposed to see, what you're supposed to look at is like if you look at my cursor right down here, that little end point there, that little point might be like a house. It might be the LAN in a house, and it connects to a router, which connects to a router. And each straight line is supposed to be like a connection to another router. And you get up inside of this entire crazy network of routers connected to routers connected to routers. Okay, and then maybe eventually you'll exit out here somewhere. Okay, and you'll exit out there, and that's your destination where you want the information to go. Destination could be like, I don't know, you're shopping on Amazon, so that destination might be like www.amazon.com. Okay, and or if it's a text message, that's like the phone number of the where the message is supposed to go. It's like literally any information that's passing out of the internet, or passing out of your phone or out of your computer into the internet. Okay, and then of course they got to answer back, and the answer will go through this mess of wires again, wires and radio waves and satellites and fiber optics and so on, and then it'll eventually through the routers bounce back and come back to your computer there like that. Okay, so that's how the internet works, and you can think about it in a slightly different way. You might say, well, how does my particular information get through here? And this picture here, also from the same page, okay, kind of shows that. So like you are on the internet, okay, and you're going to go to somewhere else on the internet. Okay, and what happens is your computer will, like, see where my cursor is, suppose your computer's somewhere here in this cloud of internet. Okay, and you construct a packet, which is basically, it's a package of information, and I'll tell you what's in a packet in a minute, but just think of it as kind of what you could think of it as is like a letter that you're sending through by snail mail. Okay, and the packet first goes to your ISP through a router, okay? And what an ISP is, it stands for Internet Service Provider. This is the company that brings the internet to your house. All right, so we have two major companies around here. Verizon, that brings the internet to your house via Fios, which is a fiber optic cable, and Spectrum, which brings the internet to your house through cable. Okay, like television cable. All right, and these ISPs, they're pretty big, but they don't cover the entire world. It's not like the whole world has Spectrum. Okay, like another ISP might be like Comcast or something like that. All right, so they themselves have an even higher level ISP, and the information then will go up to the next level. So through a router, it'll go up to the next tier and eventually up to the tier 2 networks. Okay, and these are going to be like the really big networks that they almost span the globe. They might be like Verizon itself is a phone company. It's like these are the kind of the huge telecommunications company. Okay, but they themselves might not be the biggest. So there's a tier 1 level network, and these are the ones that really connect everything. They're like the backbone of the internet, if you want to call it that. And then, of course, once your packet has gotten up into a tier 1, it's got to descend back down to where its destination is. Okay, so let me trace that out again. Here you are. You send it to a tier 3, which is like your internet service provider, and then from there you go to a tier 2, okay, which is like one of these telecommunications companies, and then you go up another level to like your tier 1s, which span the globe, and then of course you go down into another tier 2, okay, and that'll go down to a local ISP for your destination. All right, not your ISP, but the ISP of the destination, and then that'll eventually go to wherever the destination is here out on the internet. And then of course they'll send a packet back, they'll send a packet back, they'll send a packet back, and it'll retrace its path from where it came. Okay, and so that's just an overall picture of how this internet works. Okay, now I should tell you a little bit about how your computers in your home or your classroom or dorm or whatever, or if you're like at the college, the college's LAN. Okay, how does that actually get out on the internet? Like, what is that device? Okay, like I'm thinking, at some point you might have a home, and in your home you're going to have a router. What is this thing? What does it look like? Well, the ISP might install it for you, but you can, for a slightly cheaper price, buy your own router and attach it. Okay, I rent my my router from Spectrum. Okay, I have Spectrum here, and here's an example of a router. Okay, so let me bring that picture up, and I just picked one product among many. Okay, this is a router which is a combination cable modem and 4-port Ethernet, and as you can see, it's like it's supported by Comcast here, or Spectrum and Cox, which are again ISPs. And you wonder, what are you looking at here? Okay, so there's a few things to notice in this diagram here. First, the yellow ports here. These are what are known as RJ45 jacks, and basically that's where the Ethernet cables get attached. If you've ever seen a computer attached to the internet via a wire rather than wireless, via a wire, then the wire gets plugged into one of these 4 ports here, and they're all equivalent to one another. Okay, and the modem. The router will then pass that out to the internet through this circular jack here, and that's basically your cable port. So your cable screws into that. Now, you've heard me say a minute ago that this was a router and a modem combination. So you might wonder, what's a modem? So router basically passes around that information, these packets. Okay, a modem. And you can have router modem combinations like this one. A modem actually converts from one type of a physical layer, it's called, from one type of medium which carries the internet to another kind. Okay, so here on those yellow ports, they are basically Ethernet cables. Okay, again, those wires that you see, sometimes computers are attached to the internet via these wires. At the college, they're usually blue, but they could be other colors too. Okay, now that's one kind of medium. That's one kind of like physical material that you can pass through. Cable is a different one. And so whenever you go from Ethernet to cable, you need this thing called a modem, which converts between the two. And so there's a cable modem, which is this one, which converts cable to Ethernet, okay? And there's also a fiber optics modem, which, people that use Verizon have, and they'll convert from, the fiber optics medium to the Ethernet medium. Okay, so that's another layer I just thought you should know, because most homes have a combination router modem, but the important function here is the modem, because your computer out here somewhere will communicate via wire into one of these wires, and then this modem says, oh, what do I do with this? And it says, oh, I have to send it out on the internet. It might send it locally, like it might go in here and then be sent locally, because if it's on the LAN, there's no reason to send it out on the internet. But it might take your packet and pass it out through the cable here. And where does it go? To the next router, the router at your ISP, that tier 3 router that I was talking about a minute ago. Okay, and then that router will take care of it from there. And it's kind of like the U.S. mail system, like the snail mail system, where one sorting station in snail mail will send it to another sorting station. That's where they take care of the mail to decide where it goes. And they keep passing the mail around from city to city to city, from each of these sorting stations to another, until your mail eventually gets to to its destination. And that's exactly what the internet does. Only these are computers, and they're working millions of times faster, even billions of times faster than humans. So it doesn't take 3 days for a letter to get or a packet to get where it's going. For these guys, it takes, in the milliseconds. And milliseconds are thousandths of a second, okay? 1 millisecond is like a thousandth of a second. So it's not unusual for a packet to get to its destination in maybe 50 milliseconds, okay? 50 thousandths of a second, which is really fast, okay? And that's what, why, when you're surfing the internet, the information seems to be coming down to your computer fast. Not infinitely fast, but pretty fast. Okay, and so there you go. This is a modem. Okay, and so I mentioned here that most home modems are a combination of actually 3 things. All right, so right here, most home modems are a combination of 3 things. They're a router, they're a modem, and then there's the third thing, which I haven't mentioned yet. They're wireless. The modem that I just showed you, the modem router combination that I just showed you, was purely wired. In other words, it doesn't work unless you plug something into it. But there are some modem routers that will do all 3 things. They're a modem, so they convert between cable and Ethernet, okay, or cable and wireless. They're a router because they connect LANs, okay, they interchange packets between LANs. And they're wireless because you don't have to plug a wire into them. You don't have to plug a wire into your computer and then plug a wire into your into the router. Those are called, by the way, Ethernet cables. Okay, you don't need an Ethernet cable. It could just go through the wireless. Okay. And so a lot of modem router combinations for your home are like that. Okay, I didn't show you a wireless. They have the antennas. The reason is that particular picture, you could see the back of it very nicely. Some of the other pictures weren't quite as good, and I wanted you to see where you screw in the cable. Okay, because cable's kind of a roundish, a thick round cable that you screw into the back of it. Okay, and it's a coaxial cable. All right, so there you go. You've got a bit of an idea now of how this internet works, and let's dig a little bit more into the details of these packets. Okay, and again, I'm not doing this to overwhelm you with just extra technical details. Believe me, the amount of technical details that I'm jumping over is enormous. The internet is an absolutely amazing engineering feat, okay, that we've been working on for about 30, well, maybe more now, about close to 40 years or so, okay? So, yeah, I'm skipping over a lot of details. These details are just so you have a good idea, so that you have a good sense of security, okay? And you're not using the internet naively. Okay, so these packets, what are they? When you go and say you're downloading a web page, you click on a link, and this web page is, being brought up and rendered by your browser so that you could see it. Okay, being displayed by your browser. There might be dozens of packets going back and forth for that web page. Okay, so the web page isn't just one packet; it's a bunch of packets. Okay, and each packet is basically like a little envelope. All right, and so there are 3 things in an envelope if you want to send it out on the mail. So I'm using the metaphor of the mail system, the snail mail system. There's at least 3 things that you need. The first thing is you need a destination address. Okay, in other words, like if you're sending a letter and you want it to get to a destination, I don't know, to some home or like to Juval College. Okay, if you don't write the address of where you're sending that letter to, and you put that in in your mailbox, the mail person will look at this and go, I have no idea where this is going. I don't know what to do with this. Okay, and so just like snail mail, these packets have to have a destination address. Okay, and that's known as a destination address. Okay, so that's one thing that these packets absolutely must have. All right. Another thing that these packets must have is what's called a source address. Okay. Now we usually don't call that. Usually don't call a return address a source address, but when it comes to computers, they're called the source address because that's where the packets originate from. Okay, but we usually call them, like when we're sending out snail mail, return address. Okay, so you write that in the upper, what's that? The upper left corner. You write your address where the letter is to return to. Okay, and this makes perfect sense. Think about it. If you don't put a return address and it gets to its destination, how does the destination know where this came from, and how does it know how to answer you? Okay, so that return address is kind of important. Okay, so once again, there's a destination address, that's where it's going to. There's a source address, which is where it's coming from, which is you. Okay, and then finally, there has to be some contents. Okay, the contents of the communication. We'll just call it the contents. I mean, you could send a letter and you just put the destination and the source address on there, and you don't put anything inside the envelope. You close the envelope, you put it in the mailbox, and it gets to the other end, and the other end opens it up and goes, what happened here? This envelope is empty. You could do that, and you can even do that with packets on the internet, and computers sometimes do that, but for very special reasons. But most of the time, what happens is the computer needs to communicate something to the other side. Something like, if you're a browser, okay, like Firefox, Firefox has to say to the other side, send me that picture because I need to put that picture, in this web page, okay, or send me that web page, okay, or something like that. So your computer is asking for stuff, and so it like writes a letter, okay, the contents, and it puts it inside this packet and sends it along, and then say you're going to Amazon.com, Amazon sees that, the Amazon servers see that, and they go, oh, you want this picture. Okay, they take that picture, put it inside of a packet, and then send it back to you. And so the exchange is going back and forth, back and forth, back and forth like that. Okay, so those are the three elements that a packet is made up of. Again, there's a lot of technical details here that I'm skipping over. Those are the three that you should really know about. And these other technical details, they do have implications for security, but we can only go so deep in a course like this. Okay, so this is good enough. All right, so now you got a little bit better idea of what these packets are about, and the next thing that you should know about is, what do these addresses look like? And here we start to see where the security comes out, because those addresses, especially that source address, that's you. Okay, and whoever can see that source address can see your address, and you can think of this as kind of like your home address. Okay, would you want everyone to know your home address? I don't know. I mean, you would certainly want whoever you want to write back to you to know your home address, otherwise how could they send you something? Okay, I don't know, an example, Juval College, you write a letter to Juval College. We don't do this anymore. We don't use snail mail. But suppose you were like old school and you wrote a letter to Juval College. Well, Juval College wants to send a physical letter back to you, a snail mail letter back to you. They need to know your address, otherwise it can't get back to you. Okay, but you may not want just anyone to know your address because, I don't know, just for reasons of privacy. Okay, but nonetheless, your home address is public. It's right outside your house if you live in a house. Okay, it's public. Okay, and so these addresses are out there and they can be used to identify you. Okay, which is the next kind of where I'm heading with this. Okay, how do you get identified by this source address? Well, the first thing is you need to know what this address looks like. Okay, so you need to even know what a source address looks like. Okay, and they look kind of something like this. All right, they look like that. Okay, so that's an address, and I think that was an old address for Juval College. It's not the current address, but it was an old address. Okay, and that's known as an IP version 4 address. There's actually two different types. There's an IP version 6 and there's an IP version 4. Okay, so these IP version 4 is by far the most common. All right, and so an IP version 4 address is made up of 4 numbers: 1, 2, 3, and 4, like that. Okay, and each of those numbers has to be between 0, that's the smallest it can be, and 255. You can't be bigger than 255, okay? And so the combination of those 4 numbers basically gives you a an IP version 4 address, okay? They're by far the most common, okay? There is a new type of address, and it's becoming increasingly popular. They're known as IP version 6 addresses. They're a little bit harder to see. They look like this, okay? They're a bunch of numbers and letters, okay? And you go, letters and numbers? Yeah, if you think about it, those are hexadecimal. So you remember the hexadecimal numbers that I kind of mentioned when we were doing binary? Those numbers, hexadecimal numbers, like the digits, go between 0 and F. And you go, what, 0 and F? Yes, because remember, once you get to 9, you don't stop. You have 16 unique digits. And so what those unique digits are, single digits, 16 unique single digits, what are they? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. Okay, so between 0 and F, there's 16 unique symbols. Okay, so every one of these digits here, like that F, that's a hexadecimal digit. Okay, and then there's an E, another hexadecimal digit, an 8, and then 0. And then there are these colons, okay, and then there are more hexadecimal digits like that, okay? And it's not important that you know the details of how to interpret these. The only important thing so far is that that you can recognize one. And the reason you want to be able to recognize one is because you can then say, that is my IP address. That's how people in the world know it's me. Okay, and I'll show you in a minute how to identify your IP address. Okay, as throughout this lecture, I'll show you, how you can find out what your IP address is, because that identifies you. Okay, but before we get there, you need to be able to do a little bit of interpretation about what's going on. Okay, so those are the IP addresses, and that's who you are. Okay, and so great. Now your computer is constructing a packet, and it's constructing a packet, and it says, okay, this packet is supposed to go to Amazon, and so it writes as the destination address the IP address of Amazon.com. Okay, and I'll show you in a minute how it gets that IP address, but it knows, your computer can find out what the IP address is for Amazon.com. It also knows your own IP address, and so it writes its IP address, your personal IP address, source IP address, on the packet, and then it sends the packet along the way. Okay, and then it gets to the destination and comes back. Okay, now I'm going to say a little bit more about these IP addresses in a minute. Okay, but at this point, that now you understand a little bit of how this technology is working, let me show you the first kind of insecure thing that can happen on the internet. Okay, now you don't have to worry about fixing this. So when I tell you about these insecurities, don't think that this is something you have to fix, but this is something that engineers had to fix on the internet, and it can break sometimes. So it's good to know about it. Okay, and this is what's known as the so-called man-in-the-middle attack. Okay, and what does that mean? Well, remember, when you send that packet, think of it like you're sending mail on the through snail mail. You put it in the mailbox, and it a mail person comes along and gets it, and then sends it to the next person, the next person, the next person. Your mail passes through the hands of many people before it reaches that destination. And here's what you're hoping. You're hoping that no one's going to open up your mail. Okay? Like the post office isn't going to open up your mail. Like some mail person opens up the mail and reads it. Okay, could they? Yeah, they could, but then you would see that the envelope has been cut open. But on the internet, you can look inside the contents and not know that this packet has at all been disrupted. Okay, and so this is the so-called man-in-the-middle attack, and this is the wiki page for man-in-the-middle attack. Okay, so let me just scroll to the top here. Okay, and again, more detail than you need. All right, so and just for reference, if you really want to know how this is done, okay, it's a form of eavesdropping. Okay, and they discuss it in here. So basically, someone is snooping on what you're writing. Okay, or what the communication is, what kind of communication you're having with the destination. Okay, and it's really simple. Okay, there's this picture here. Let me make it a little bigger for you. Okay, and this is about as simple as possible. Alice wants to talk to Bob. Okay, and Alice and Bob are good. They're blue. Okay, and in between, Alice can't get the letter directly to Bob or the information directly to Bob. In the middle, there's Mallory. and Alice has to trust Mallory, and Bob has to trust Mallory. And if Mallory is malicious and wants to read the contents, that they can. Okay, and so it's as simple as that. Okay, and Mallory, they don't have to touch the source or destination address. Okay, because Alice says this is destined for Bob, and Bob says this is destined for Alice when Bob responds, and Mallory knows that, but it has to pass through this middle router, Mallory. Okay, and there you go. That middle router, has a human engineer that's running it, and if this human engineer really wanted to look at the contents of your packet, they could. Okay, the technology simply allows for that. And the reason is, you say, well, why did we build the technology that way? Because remember, in the early days of the internet, all right, no one was ever thinking of using it for business or anything like that. These were mostly engineers, physicists, mathematicians, that were passing their data on the internet. They were geeks. Okay, they were the early geeks, and they were just passing this information on the internet. And if someone wanted to see that information, they certainly could. So I didn't tell you my background, but my PhD is actually in theoretical physics. And I mean, I remember like in the 80s sending emails to people and was totally insecure, but I never thought that what I was sending would at all be sensitive information. I was just writing about my research and sending data back and forth, and no one really cared to look at this stuff, and then if they did, it had no consequences. But today, a man-in-the-middle attack would be absolutely devastating, because if someone got your username password for your bank account, it's game over. Okay, they get into your bank account and they can do all sorts of, they can steal all $100 that you have in your bank account, right? So, the internet started very naive in its construction, but it got better and better and better because we had to solve these problems. Okay, so so these IP addresses, back to the IP addresses, they're pointing out the destination, but remember, just because they're destined for that final point, they do pass through the middle, and that's one thing. So the content can be seen, and also the source and destination address can be seen, and so whoever does this man-in-the-middle attack knows three things, all three things that are in the packet: who it's coming from, who it's going to, and what you're saying to one another. Okay, very insecure. Again, as we go on, I'll show you how this gets secured in the internet, but that's like ground zero. Okay, let's go back to these IP addresses. Okay, and let's take a look at them. So there's this IP version 4 and IP version 6. Okay, the IP version 4, they're the older ones, and they're kind of falling out of, they're still in use, and they're still the most popular, but they're kind of falling out of use. They're decreasing in popularity, and the reason is that we've run out of them. We've literally run out of IP version 4 addresses. Okay, so IP version 4, the number's written like that, but if you were to convert those decimal numbers into binary, the binary number that corresponds to this address 67.222.116.19, it would be 32 bits in size. Okay, so do you remember, like when we were doing the binary numbers, if you had a number which was 32 bits in size, you might ask the question, well, how many things can I encode with 32 bits? And we actually had a 32-bit encoding, and that was Unicode. And with Unicode, you could encode 4 billion things, because 2 to the exponent 32 is 4 billion. Okay, and so there are 4 billion different IP version 4 addresses. Now think about this. You have to have a different address for every single computer on the internet, because if two computers had the same address and a router got a packet that was destined for that address, it wouldn't know whether to send it to the one or the other, because they both have the same address. And so this router gets this packet, and suppose this packet is destined for 1.1.1.1. And there's two computers that have the address 1.1.1.1, and both computers will say, I have that address, and the router goes, well, I don't know which one to send it to. Okay, so every computer on the internet has to have a unique IP version 4 address. Okay, there are only 4 billion of them. They say only 4 billion. Yeah, I mean, when IP version 4 was first invented or first, designed, they thought that 4 billion was going to be more than enough. Okay, but there are more than 4 billion people on the earth right now. Okay, and everyone has one of these, right? Okay, so we've run out. It's as simple as that. We simply ran out, and it happened like I forget how many years ago, but it was not that long ago, where literally the consortium that was responsible for allocating IP version 4 addresses said we're out of IP version 4. Okay, and so we saw this coming for a long time, and so that's why IP version 6 was designed. And IP version 6 is a whole different beast. I mean, like this is like Unicode on steroids because it is 128 bits in size. Okay, and that's like 4 times bigger, like 32, 32, 32, and 32. So that's like, 4 times 32 is 128. All right, and if you take 2 to the exponent 128, okay, because that's how many addresses you have in this space, it turns out in decimal to be 3.4 times 10 to the 38. Okay, that's like a digit followed by 38 other digits. Okay, or sorry, a decimal number with 38 digits in it. That's absolutely huge, absolutely huge. It's unimaginably big. Okay, now the reason we made it this big is so that we would never run out. Okay, and it's so big that the consortium that's responsible for handing out IP version 6 addresses is just handing them out like candy. Like I mean, once I asked for a 64-bit block. Okay, now a 64-bit block, that's already twice the size of a 32-bit block, but that's not twice as many addresses because it's 2 to the 64, and 2 to the 64 is huge. So it's like 4 billion times 4 billion. So I had 4 billion times, just to me, just allocated to me, were 4 billion times 4 billion addresses, 4 billion times as many as there are IP version 4 addresses. Okay, a mind-boggling number. Now that was just to me, but because IP version 6 is so big, they could do that for they could do that for everyone in the world, and they wouldn't run out. So we made it so big that you just won't run out of IP version 6 addresses. Okay, now you need to know what these addresses look like so you know what you're being identified like on the internet. But there's another reason I'm telling you this. Okay, and that is because IP version 4, because they were running out. This is a little bit hard to understand. Because we were running out of IP version 4, what they did is they took a little chunk of IP version 4 and we said these addresses will never be used on the internet. Okay? So they actually made the space smaller. And you go, why did they do that? Because what they did is they allowed for those private IP addresses, as they're called, to be recycled. Okay? And so on a LAN, on a local area network, you can have the same IP addresses as on another LAN. Usually they look like 192.168.0 something. Okay, but there's others. Okay, so anything that begins with 192.168 is a private IP address, private block of IP addresses. And by allowing this recyclability, it meant that on a LAN you can have hundreds of devices which are using an IP address that other devices in the world might be using as well. So these are recyclable. So these private IP addresses are recyclable. So there's 2 parts to the IP version 6 space. There's those which are public and those which are private. The private ones are recyclable and the public ones are not. The private ones can be recycled on LAN, on all the different LANs. Okay. And you say, well, how does this help the problem of a scarcity of IP version 4 addresses? And the answer is because the LAN passes through one router. And only that router has to have a public IP address. So the public IP addresses have to be unique because they have to be able to route on the internet. Just like I said a minute ago, they have to be unique. Otherwise, other routers will get confused. Where do I send this? So your router, the part of the router that faces the outside world, that faces the internet, has one and only one public IP address on it. The private side, the side that's on the side of the LAN, has hundreds of IP addresses. So these hundreds of IP addresses are sharing one public IP address. Okay, and the router is responsible for keeping it straight. Like when the packet comes in, it knows that it came from this device and not another device on the LAN. Okay, so the router's smart about, once the packet comes back, the router's smart about which private IP address to use. But the outer face, one public IP address. And so suddenly now hundreds of devices could be sharing one IP address, and this is how life got easier. Okay, so once again, the entire IP version 4 address space got divided into 2 parts, a public part and a private part. The private parts are used on LANs. Okay, the private IP addresses are used on LANs, and they are recyclable, meaning you can have them repeated. Okay, The public ones are used on the outer side of the router, the side of the router that faces the internet, and there's just one. Okay, the public IP addresses have to be unique, routable, and the private IP addresses can be recyclable. And this allowed for more devices to be on IP version 4 than you might have. If every single device had to, have its own private IP address, public IP address, then we wouldn't be able to do it with IP version 4. You'd run out. So the college actually has one public IP address, but there are hundreds of computers at the college. Each of the computers at the college have private IP addresses that are recyclable, but they're all sharing one. So suddenly 100 got reduced down to just one, and that conserved some of the IP version 4 addresses. And at this point you're saying, well, why did I tell you that? Because it means you get a little bit of privacy, okay, on IP version 4. Behind the router, the outside world can't tell which device the information is coming from. It could be coming from you. It could be coming from your friend that is using the same private LAN, private IP address. LAN with same private IP addresses. Okay. As far as the outside world is concerned, it can't see all the devices behind your router. Okay, because they're all private IP addresses. Okay, so that gives you a little bit of anonymity. Okay, if you're surfing a web page at the college, that web page can't tell if it's coming from you or from your neighbor on the same LAN. Okay. Nonetheless, you can't be naughty, because the person who's responsible for that LAN, all right, the person who runs Juvo College's network, internal network, would then be able to figure out who you are, okay, because these things get logged, okay? Now, if they're not logging them, that's a different story, but they probably are. And then they could say, I was this person, who did this naughty thing on the internet and not this other person, okay? But still, as far as the outside world is concerned, they can't tell one device from another on the private network. Okay, so IP version 4 has this extra little layer of privacy. Not perfect privacy, but some privacy. IP version 6 does not. Okay, if you think about it, every single IP version 6, every single device in the world can have its own unique IP version 6 address, because there's more than enough. Okay, now this is a known problem. And so there have been ways of trying to create privacy. I don't want to get into that right now, because this technology is kind of emerging, and it'll probably take a few more years before it emerges. But yeah, there's less privacy with IP version 6 than IP version 4. But IP version 6 is the future. And the internet always starts naive and gets more and more sophisticated in terms of security and anonymity. Okay, and so really the only thing that's mostly holding us back from IP version 6 is people don't want to switch, and they're not sure what the switch means. Okay, and so yeah, that's coming, and it's just good to know. Okay, it's good to know. All right, so at this point I'd like to demonstrate some of this stuff for you. Okay, and I can do that by taking a look at this. Okay, you're saying, what am I looking at here? Well, let me just clear that out for you. Okay, right now what you're looking at, actually, let me just squeeze it down a little bit like that. Good. What you're looking at is basically a terminal on a server that I have, which I believe is in New Jersey. I don't know. I just pay for like $25 a month for this tiny little server. It's actually a virtual server. Okay, it runs on a virtual machine. Okay, and this particular server, I just use it to put some of my stuff online and so on. But it has its own IP address. So let me show you that. So this is not like a web page, but I can type a command in here, ifconfig, okay? And you don't have to memorize these commands. And what it does is it tells you all the IP addresses that are available on this machine. There might be more than one, okay? And so if you take a look here, that right there that I have highlighted, that is the IP version 4 address for my server, okay? It never changes. It's a public IP address. Okay, and that server's always sitting there on the internet. Okay, and now if you take a look, you'll notice that it has two IP version 6 addresses. There's one, and there's another one. Okay, now I don't want to get into the details here of the difference between the two, but this one is what's known as a linked local. It's not used for routing on the internet, but this one is. Okay, and so there is a second way that you can get a packet to my computer, to my server, okay? Either via IP version 4 or via IP version 6. Your device, your phone, your computer, whatever, can have both an IP version 4 and an IP version 6. It could have just one, It could have the other, or it could have both. Okay, and since my, I want my servers available as possible, I have both IP version 4 and IP version 6 addresses. Okay, and then there could be other addresses here, but these addresses are just local addresses. So that's like a local address, and that one is another local address that I use for a VPN. That's like a private way of communicating, like a little backdoor to my server, okay, and some other computers, okay. But that's not what I wanted to show you. It was this one, okay. And so every device which is on the internet publicly, directly, like a router or server and so on, they're going to have that public IP address. And any device which is on a local network is going to have an IP address like this, okay. And you could see it starts with 192.168. That's, again, this kind of like little private network that I have, and only my own computers can talk on. It's a LAN, okay. It's like a virtual LAN. Okay, so that's the first thing I wanted to show you. The second thing I want to show you, and we'll talk about DNS next, but I want to show you how my computer gets to Duval's computer, okay? So my computer has this IP address there, okay? And Duval's computer has this address, and I'll show you right now. It has this one. Okay, there it is right there. Okay, now how I converted between the name www.dyc.edu to the IP address, we'll talk about it in a minute. It's called DNS. But right now, what I just wanted to show you is that number that's highlighted right here, that is Duval College's unique public IP address. Okay, 199.212.95.2. Okay, the next thing I'm going to show you is what's called a trace route. And so I'm going to send a little packet from my computer to Duval's computer, and I want to trace every single router that it goes through. Okay, now this sometimes takes some time, and I think it's going to time out, but we got enough information. Okay, and you go, geez, what am I looking at now? Well, what you're looking at now is the hops between router to router to router until you get out into the internet and to Duval's computer. Now, some companies don't like you trace routing, and that's why you see these asterisks here. But let me explain what you're seeing. My computer, in order to communicate to Duval College, first passes the packets from this address here, okay, from that 5116.55.85, from there to the first router. There you go. There's the first router that it gets to. Okay. And then that router passes it to another router. And that router passes it to another one, and then to another one, and then to another one, and then to another one. And now we're 6 hops out. Okay. And then router number 7 says, I'm not going to answer you. Okay. And the reason that router did that is just because it kind of like, it's just for privacy reasons. Okay, I don't think it's that big of a security risk, but nonetheless, that's what that router did. Okay, decided I'm not going to respond. Okay, the next router said, okay, I will respond, but then all the routers after that decided not to respond. Okay, and so unfortunately, we can't see that full trace route. We could do the same thing to say Google. Let's look at Google's IP address. Okay, so Google actually has 2. Okay, an IP version 4 and an IP version 6. Duval's a little bit behind the times. It has only an IP version 4. Let's do a trace route. Let's see. Oh, there's a trace route 6. I haven't done this. Let's see. So we're doing this for our first time. Let's see if this works. Oh, yeah, that was perfect. Yeah, in 6 hops, we got to Google. Okay, so my computer from my server, from this address right here, okay, so that's the source IP address, passes it to this router, which passes it to that router, which passes it to that router, then that router. And now we're four hops out, 5 hops out. And then finally we get to hop number 6. And hop number 6 is Google, because if you take a look at that number and you take a look at that number, you see that they are the same. Okay, they're the same IP version 6 address. Okay, and so there you go. There's a demonstration of the mailman system of the internet. This passing of packets between router and router and router. Do I trust these people? Well, I don't know if I have a choice, but the person that runs that router, I mean, there's a human being behind that. They could, if they wanted to, look at my packets as I pass them between my server and Google. And this person could do the same. Okay, and that person could do the same, and that person could do the same, and so on. Okay, and there it is. Okay, last thing I'm going to show you before we switch back to the notes here is you'll see these numbers here, and you go, well, what are those numbers? They are actually a measure of how long it takes for a packet to get to that router. Okay, and there's kind of a low, a medium, and a high. But if you just take a look at that middle number there, that's kind of like an average. That's like let's just round it off to 1.2 milliseconds. That's like a little bit more than a thousandth of a second. Okay, so a little bit more than a thousandth of a second to get to the first router, and then like even less to get to the next router. Whoops, right here. Okay, like a little less than half a millisecond there, and then a little more of a millisecond to go from like the second to the third router, and so on. And so if you add up all the milliseconds here, and the last one here seems to be like like about 1.4 milliseconds. But if you add that up, that's under 10 milliseconds, and around 10 milliseconds. Okay, but 10 milliseconds, 10 thousandths of a second, that's a hundredth of a second. Okay, that is so fast, no human being can see that happening. And so any web page that's coming down from Google through this route is simply just going to appear in my browsers almost like instantly. Okay, so there you go, kind of a real life demonstration of what's going on. By the way, if that all looked too geeky to you, don't worry, I am not going to make you repeat any of that. I just wanted to show you that this is very real, okay? And that you can identify the routers between yourself and the destination. And the people that are running those routers, what can they see? They can see the source IP address, they can see the destination IP address, and they can see the contents, okay? And the contents, you're a little worried right now because they're going to be carrying your username password. Don't, because we're going to look at encryption in a minute. And that was the first thing that we had to do on the internet before it was useful for business. Okay, because if you can't encrypt your communication between you and whoever you're doing business with it's game over. Anyone could get your password, and I'm sure most of the people working at these companies, they're ethical people. They're not going to steal your information, but all it takes is one. Okay, and I've run routers before, and it's hard for someone to know if you're cheating. Okay, if you're looking at something that you're not supposed to. It's illegal. I don't know the laws, but I'm pretty sure it's illegal to just start looking at people's private information as it passes through the internet. But there's always going to be someone out there to do that. Okay, all right. So next thing is DNS. This is another piece of information that you need to know about. Regarding what's happening with your information on the internet. Okay, so DNS stands for Domain Name Service. Okay, and it basically is how you translate the names of computers into those IP addresses. Like I don't know, you may not have ever known about IP addresses before this course or before this lecture. You might not have known that you had an IP address. You might not have known that Jewel has www.dyc.edu has an IP address associated with it. Okay, how do you know Jewel's webpage? Well, you know it as www.dyc.edu, and since www, most web pages start that way, people will just say dyc.edu, okay, or google.com, or with Google it's even shorter. We'll just say Google. So humans think in terms of names, the names of things. Okay, and computers think in terms of IP addresses. You could think of them as like a name and a phone number. Okay. Now, no one memorizes phone numbers anymore because they're stored inside your phone. But, memorizing a phone number is pretty hard, okay? And so people think in terms of names, and we tend to look things up in terms of names. And, once upon a time on your phone, like the ancient phones, you actually had to have phone numbers memorized, okay? And then you could call those numbers because you'd have to type one in. But now we have contact lists, like you have your contacts, and you could just look up a name, and your app will convert the name into the phone number for you. Okay, you don't even have to see the conversion; it just happens behind the scenes. Call Fred, call Mary. Okay, you click on call Mary, and then the number appears in your phone app. All right, so there is a phone number there. You do see it, but you don't have to memorize it. And the same thing is happening on the internet. But there are billions of names out there, and IP addresses associated with those names. And like, how does that work? Well, basically, there's a huge phone book in the internet, okay? And it's a distributed phone book, which means no one computer is responsible for keeping all of it, but they share the information between one another. But this phone book is called DNS, domain name service. Okay, and we don't call it a phone book. That's an analogy, but basically it is the mapping between the domain names like www.dyc.edu and the IP addresses. Okay, and when your computer constructs these packets, it has to have the IP addresses. You might type in the domain name, or you might click a link and that link has the domain name in it, but then behind the scenes this conversion has to happen. Okay, and who's doing that conversion? Well, your computer is asking other computers out on the internet to do that conversion for you. These other computers that are doing this, they're not the routers. They're another set of computers. Okay, they're called domain name servers, and these domain name servers are basically doing the conversion. So your computer does something like this. It says, suppose you put www.dyc.edu. Your browser, Firefox or Safari or whatever you're using, or Microsoft Edge, it says to itself, it has like a local cache, like a local list of conversions between domain names and IP addresses, so that it doesn't have to ask all the time. It first looks in its local cache, okay, and it looks locally, and it says, "Do I know this already? Did I just write this down a minute ago?" And do I know that IP address so I don't have to ask someone? And if the answer is yes, your computer doesn't ask anyone because it was right there inside the cache of the computer itself. Okay, cache is like where you store stuff. Okay. But if it doesn't, if the browser says, "Oh, I don't know this one," then it's got to ask a domain name server. The first domain name server that it asks is your ISP. So your ISP not only gives you, a router, but and connection to the internet, it also gives you some services. And one of the services it gives you is DNS. It might even give you email and other services. So think of DNS as like kind of an email that happens behind the scenes. Okay, and so your computer will ask your ISP, and your ISP might say, "Yes, I know that one," or "No, I don't," and then it might have to ask another computer. Okay, and then it might have to ask another computer, up to 3 levels, 3 tiers again. Okay, not to be confused with the 3 tiers I showed you a minute ago of the 3 tiers of the routing. This is 3 tiers of DNS. I'll show you a picture of that in a minute. Okay, and one of these computers are going to know, and then the information trickles back down to you, and then your computer knows the IP address, it can go there. Now, why is it important to know this for security reasons? Because you're leaving a trail. Okay, you are leaving a trail with these DNS servers of what websites you are going to. Okay, now it's not a perfect trail because your computer might already know the IP address and it doesn't have to ask. But every time it has to ask, like it had to learn it, for the first time. So at least once it had to ask a DNS server, "Hey, can you give me the IP address for this domain name?" And so you're leaving these like little breadcrumbs, and you're telling these DNS servers basically what websites you're going to. Okay, and there's no way around this because there's no way that your computer could have all like billions of names. It would be so much information your computer can handle it. And then it's not just that, but the information's changing all the time. So your computer would be forever updating its DNS list. Once upon a time in the early days of the internet, we're talking the 80s. Yeah, they would be like these lists, and every computer would have that list. But nowadays, no, this is a distributed system throughout the internet, and you're leaving these little breadcrumbs. And just recently, like I think about 3 or 4 years ago, it became legal for these DNS servers to sell these lists of DNS requests, okay, as part of like marketing and stuff like that. Now, they wouldn't sell your IP address. They were supposed to pull out your IP address so that it became anonymized. But, like that's getting a little bit annoying that, you're just leaving these breadcrumbs behind, okay? And so there's the story behind DNS, okay? And let me show you, roughly how DNS works in terms of a picture here. So let's go to there we go. Okay, so this is the Wikipedia page on domain name service or domain name systems. Okay, and way more information than we need. There's some nice pictures here, but the picture that I really want to show you is I guess way down here. No, one more. There it is. Okay, so what are you looking at? here you are. This is you, email client. That just means like your email. Like a lot of people go through the web page, so you know, you don't even need the email client. Just think of it like your web browser, okay, like Firefox or whatever you use, okay. And the first thing that your browser does is it asks for what's called a local resolver. That means like your local computer. So basically, your browser says to your own computer, "Do you know this IP address?" And then your computer looks in that cache and it goes, oh, sorry, in its own cache right here, local cache. That's this part right here. It goes, yeah, I know the IP address, or no, I don't. Okay, and that's just happening locally within your computer. And so a lot of times, because you just went to like Amazon.com, you know Amazon.com, or your computer knows the IP address for Amazon.com. It doesn't have to keep asking every time. Okay. Eventually, though, the cache gets emptied. Okay. And at that point, your computer has to ask the next level up, okay? And this is known as a caching resolver. This is like what your ISP will be running, okay? And that has like a multi-user cache. It means like it's not only caching for you, but it's caching for like everyone that all the customers of your ISP. Okay, could be like thousands of users that are just using this. Now, chances are it goes up to that far and no further, because you know how many people use Amazon, go to Amazon.com. Okay, it's only like those rare addresses where it might have to go past that. Okay, and then to go past that, it goes to like another level up, and this is the recursive resolver, and that one goes through like a 3-tier system where it goes like to the root level. Okay, and then the root level will go to the next level, and then the next level. And you go, well, what are these levels? The first one, like suppose you're going to www.dyc.edu. The first one says, oh, you're going to an edu address? Go to this one. And then that one goes, oh, yeah, I'm an edu DNS server, and you want a dyc.edu? Okay, go to this one. And this one goes, oh, you want www.dyc.edu, and it gets the answer, and then it passes it back. So each one is kind of like a higher level. Like the top one is all of them, the entire domain name space. Okay, the next level down are like the .coms, the .nets, the .edus, and so on. And then and then the last one is like the what's called the fully qualified domain name. It would be like www.dyc.edu, and then that information gets back. And then as the information passes back to your computer, each computer makes a copy of it in the local cache, just so it doesn't have to keep asking over and over and over again. Okay, and so there you go. This is how DNS works. And again, if you go to a site and you haven't been to that site recently, you're going to go up to at least this level, which is your internet service provider. They're going to log your request. They're going to log that you went to such and such an domain name because you made that domain name service, domain name request. Okay, and so yeah, you're leaving these little breadcrumbs all over the internet, and you say, well, how do I fix that? I'll show you later. I'll show you how you can get past leaving these little breadcrumbs all over the internet. Okay, and I can demonstrate this for you on my server again. Okay, so again, here we are in this. It's called a terminal. It's actually called a shell. And within the shell environment, there are certain commands that I can state. And so I can go like host www.dyc.edu, and it answers www.dyc.edu has address 199.212.95.2. Okay, that came out of my cache. Okay, I know that because it happened recently, and also because I can use a better command called dig. Okay. Again, you don't have to memorize these commands, but what dig does, it's going to give me an answer and tell me how does it know, that, how does it know that answer? How does it know that www.dyc.edu has that IP address? And you could see that it really didn't have to ask anyone else. It just kind of gave me this answer section, okay? And again, that's in the local cache, all right? So no one outside my computer knows that I'm asking for dyc.edu's IP address. However, I can ask dig and say pretend that you don't have this in your cache. Okay, and that's what this plus trace means. This plus trace means just like pretend that you don't know about it. And what happens now is it goes through all 3 tiers of all the different levels of asking for that domain name. Okay, and so if we go way up here at the top, the first set of options are this dot here, and that dot just means highest possible level in the domain name. Okay, and these guys right here, they're all the servers that are responsible for doing the highest level domain name. Well, because I'm asking for an edu, they sent us down to the edu domain name servers. Here they are. So what I've got highlighted there are all the edu servers. And so they're the ones that know who has dyc.edu. And so one of them answers me and says, okay, we're edu servers and we know that the dyc.edu servers are right here. And there they are. Okay. And so all of those servers are responsible for giving me the IP address. And then finally, one of them tells me where www.dyc.edu is, and it gives me that IP address. If you don't have that information in the cache, each one of those servers that I just showed you has a record that you went there and asked for www.dyc.edu. Okay? And again, what's this got to do with security? Well, it's a way of, I mean, they're not doing it on purpose to spy on you, but you are giving out this information. Okay? And so you say, all right, how do I avoid this? Well, we'll get to that. But, right now you have to understand that at the lowest level, this information is being recorded on the internet. And like I said, as of recently, these servers can actually sell that information for marketing. Okay. And so that's kind of annoying, but there it is. Okay. So a lot of information so far. All right. And just focusing on, what I've told you so far as information that gets out on the internet when you're using it. Okay. The first thing that gets out are, number one, is the destination IP address. Okay, that's the IP address of the site you're visiting. Okay, the source IP address, that's your IP address. Okay, the contents of your communication, again, if there's no encryption. All right, that's pretty easy to do. So don't worry that you've been doing it wrong all this time. Okay, most browsers automatically do encryption. Okay, but we'll go over it because sometimes they break. Okay, so you'll know. And then this last one was the domain name of the sites that you're visiting. Okay. Unfortunately, as the internet became more complicated, it not only provided more features, but it also exposed more security issues. And it's been this kind of like tug of war back and forth. More features, more things to fix the security holes. More features, more things to fix the security holes. So things are always progressing, and the technology is kind of building like layers of onions on top of the older technology. And some of those layers expose your information, and some of the layers fix it. Okay, or try to, not so much stop your information from getting there, because the best security for your computer is to disconnect it from the internet, but then you can't use the internet. So you want to have it so that you can use the internet, but use it securely. And that's what's happening here. Okay, so that's why I have this point number 5. This is the other stuff. And there are things like cookies. Okay, and these cookies, they're used to basically they can be used in a nice way to make sure that, like, if you've logged into a site, but they can be used maliciously to track you. Okay, and so there's a good part to the technology and a bad part. You remember the very first lecture I ever gave you on technology? I told you that a new technology brings good stuff, but it also brings bad stuff, because technology in itself is kind of morally ambiguous. It could be either used for good or bad. Okay, like just a simple example, almost a trivial example. Is a knife good or bad? I mean, should we ban knives? Well, like, if you ban knives, then how am I going to chop my onions? Okay, but if you ban knives, you might say, well, but people stab other people with knives, so knives are bad. But you say, but I have to chop my onions, so knives are good. And technology is always like this. I mean, I can't think of any technology that can't be used for either good purposes or bad purposes. So there it is. Okay, and that's that story in terms of the internet. Okay, now. Last thing before we go, how this information is protected. There's different places where this information is disclosed. Okay, the stuff like the destination IP address, source IP address, and contents of the communication, those are disclosed to the routers. So all the routers between the source and the destination. Remember those hops in between. Okay, all of those routers can see the source IP address, they can see the destination IP address, and they can see the contents, okay, if it's not encrypted. All right, and then number 4 is being disclosed to the DNS servers, mostly the DNS servers at your ISP, but even higher, but it's mostly your ISP that where that information gets deposited and logged. Okay, and then number 5, well, it depends. Like, I don't want to expand this course like infinitely, but those cookies, there's other places still that like web servers where that information gets disclosed. Okay, and if it's a malicious, like there's these things called JavaScript. Okay, it's like a little program that runs in your browser, and JavaScript can be made in such a way that it calls a third party and like spies on you. Okay, so again, browsers have to protect against that. But again, new technologies provide new features, but at the same time, they have to be some security has to be put in place to keep those features in check. And there's features in check for that. Okay, so I don't want to make you overly paranoid, but I do want to make sure that you understand what's going on. Okay, up to this point, this is kind of like how the internet works in the raw. Okay, how do we start mitigating, or how did the engineers mitigate against some of the security issues that I mentioned to you? The first thing is protecting the contents of your packets. Okay, if it weren't for this, the internet would be nothing more than just looking at pictures of puppies and kittens. Okay, you wouldn't be able to do any business on the internet because you need username, passwords, you need to send credit cards, and all that kind of stuff that people do, and we want to make sure that this is done securely. Okay, and so at the very least, out of all that list that I just gave you, you want to be able to encrypt the contents of your communication. So if you remember when we did the operating systems last lecture, we talked about encryption, okay, how you might encrypt a USB drive. And why did you encrypt this USB drive? Well, because you might unfortunately lose it, and it might have your banking information on it. And you go, well, that was no good because I just lost all my banking information. And I called the bank and then change your passwords and all that kind of hassle. If it's encrypted, you can't get at it without a password. Okay, so you lose your USB drive and you have some sense of security or some sense of ease that you haven't lost, very important information. Okay, and so you have to do the same thing on the internet, but you don't encrypt the entire thing because you can't encrypt the username, the source and destination IP addresses, because if you did, how would it know where to go to? But you can encrypt the contents. So you can imagine in that man-in-the-middle attack, someone gets your letter, your packet, opens it up, looks inside, looks at the contents, and sees what looks like gibberish. And it says, well, okay, it's gibberish. I don't have a password for this. I can't decrypt it. Okay? But there's one really big complication on the internet, okay, that you don't have with your USB drive. The encryption that's done on drives is what's known as symmetric key encryption. Okay, well, what does that mean, symmetric? There's two things to encryption. There's encrypting it, that is going from the plain text to the ciphertext, and there is decrypting it, which is going from the ciphertext back to the plain text. If you can go from the plain text to the ciphertext and not back again, well, that's useless because you've just locked that information and there's no going back. Okay, with symmetric key encryption, the same password that is used to encrypt is also used to decrypt. Okay, now this is subtle but important, so let me say this again. With symmetric key, that's like what you do on a USB drive. The same password that you use to encrypt it, like when it went to encrypt it, you said, what password do you want? You gave it a password, and that encrypted the information. The same password that's used to encrypt it is also used to decrypt it. Okay, the same key that's used to lock the lock is also used to unlock the lock. Okay, and you go, well, that's obvious. I mean, don't all locks work this way? No, we've actually invented a new type of locking mechanism that is asymmetric. Okay, and that's what has to be used on the internet. Now, before I describe asymmetric, let me tell you why you need asymmetric key encryption on the internet. If the same password that's used to lock is also used to unlock, how would you get that key to the other side? All right, so you want to send secure information to your bank. Okay, and you encrypt some packet and you send it to your bank, and your bank gets that packet and goes, well, great, I've got an encrypted packet and I need the key. I need the key to decrypt this. Well, if you send it the key, how are you going to send it? Through the internet? That's basically the same method by which you sent the packet, and it goes by the same route. And so the same people that can get the encrypted packet can also get the key, and the key can be used for decryption, and it's game over. So let me say that again, because it's a bit complicated, but again, important. If you send an encrypted packet through a route, on the internet, and then you send the key to decrypt it by the same route. The same people that can get the encrypted packet can get the key and then decrypt it, and that was useless. If you want an analogy, that's like, suppose you're sending a box, like a locked box, and you're going to send that through the mail, and then you know what you do? You say, well, I got to give them the key to unlock this, and you tape the key to the top of the box, and the same people that get the locked box also get the key to unlock it. That was totally useless, and that's what happens with symmetric key encryption. Okay. Luckily, in the early 70s, there were some really ingenious mathematicians that found a way around this, and this is what's known as asymmetric key encryption. And the asymmetric means that you need two keys. Okay. One key locks the lock but can't unlock it. In other words, one key is used for encryption but cannot be used for decryption. Okay, so one key is used for encryption but not decryption. And then the second key is used for decryption but not encryption. Okay, so there are two processes: encryption, that's going from plain to cipher, and decryption, going from cipher back to plain. Okay, the key that's used for encryption is different than the key that's used for decryption. They're related to one another, but they are different from one another. Okay, one of them is going to be called the public key, and the other one is called the private key. So another name for asymmetric key encryption is public-private key encryption. Okay, now think about how ingenious this is. I need to send information encrypted. Okay, so what I'm going to do is I'm going to give everyone in the world my public key. Everyone in the world has my public key. I just give it out. I'm not going to show you, but I can show you a website where all my public keys are. Okay, they are public. Okay. They're just a bunch of hexadecimal numbers. They don't mean much, but my public keys are public. Okay, so I give out my public keys. Now, anyone that's out there on the internet, if they want to encrypt something, they'll encrypt it with my public key. My private key, I keep private. I give that to no one. If I give that out, it's game over. The private key is kept private. Okay, great. So someone wants to send a packet back to me, and it's encrypted with my public key. If it gets intercepted by someone, they say, well, I want to decrypt this. It can only be decrypted with the private key. Even though it was encrypted with the public key that everyone has, it can only be decrypted with the private key. And who has the private key? Me. I'm the only person that has the private key. So I'm the only person, when that packet gets back to me, that can decrypt it. Anyone can intercept the encrypted packet, but no one can decrypt it because they don't have the private key. Okay? And so that's how magic is done on the internet. All right, so that's a little bit of a brainful, but let's I think what's hard here is that when you leave your house in the morning, you've got one key. The same key that locks the lock also unlocks it. Imagine two different keys. One key locks it but can't unlock it. The other key unlocks it but can't lock it. Okay, so they're like opposites of one another. Okay, the public key everyone has. Anyone can encrypt with my public key. Anyone can intercept a message destined for me that's been encrypted with my public key. They can't read the message because it's encrypted, and they also cannot decrypt it because they don't have the private key. I'm the only person in the world with a private key, therefore I'm the only person that can decrypt it. And this is how encrypted communication is at least initiated on the internet. Now there's a lot more to this, but it was this private public key part that was important. If it hadn't been for private public keys, we would not have been able to send keys over the internet. Because if you send a key over the internet, the same key will encrypt and decrypt. It's game over. And it was people in the 70s, three mathematicians in the 70s that came up with how to do that. Okay. Now that you have that theory in mind, let me kind of demonstrate that for you. Okay. There's just one more thing before I show you this in a browser, and that is, when I give out those public keys, someone has to guarantee that that's really my public key and not someone else's. Okay. Now what I'm going to describe is horribly illegal, but you can do it because with technology, you can always abuse technology. Okay. But when I create my public key, I put my name on that public key and I say this public key belongs to Dr. Anthony Basile. Okay. But what if I lied? What if I said this public key belongs to a bank? Okay. www.keybank.com. All right. Well, then someone out there might go, oh, I want to communicate with KeyBank. I'm going to use their public key. And they use a public key that I lied. That's mine, but I lied and said it wasn't mine. So, there's a way around that. Your public keys are not really useful on the internet unless there's this thing called a certificate authority that signs them. okay? And these certificate authorities are trusted companies. Like one of them is Visa. Okay, and of course, Visa's a credit card company, and you go, well, why are they a certificate authority? Well, because it's in Visa's interest that, people don't pretend to be banks, okay, or companies like Amazon.com or something like that. So not only is my public key out there, but my public key has been signed by a certificate authority that says, yes, this really is, a public key that belongs to, Dr. Basile and not just, someone else. If I signed it and I said, look, or I say this key belongs to www.keybank.com, and I present this to a certificate authority, well, then the police are going to be knocking at my door, okay? Because the certificate authority is going to go, well, this person's lying. And you have to prove that you really are who you say you are to these certificate authorities, okay? And I actually had to do this for Duval College some 10 years ago or more. And basically, I think I used Verisign, was the certificate authority. You send them the key, and then, they call you. They call Duval College. They ask for tax records. They ask for a whole bunch of stuff to really prove you are who they are. They sign the key and then they send it back to you. When your browser gets, one of these public keys to sign stuff, it checks and says, was this signed by a certificate authority? And if it was, it'll use it. If it wasn't, it won't use it. Okay. So these public keys, like I said, they're all over the internet and they're being spread publicly, but they are also not only public, but they have been verified. Like on Twitter, how there's like some people that have the blue check mark, they've been verified. And that's kind of like these public keys, they have like a little check. Okay. And you can make public keys that don't have a verification, and I'm going to show you what your browser does when that happens. Okay. So there you go. There's the theory. And there's a couple of web pages on how that works. Okay, so let me just show you that over here. Okay, so here's public key cryptography. It's sometimes called public-private key cryptography, or just public key cryptography, or asymmetric key cryptography. Okay, so it goes by a few names, but basically, it's this idea that you've got a you can see in the picture here, you've got a public key and you've got the private key, okay, and they're generated by some magical mathematics, okay, and in this next picture down here, they show how the encryption works, and it's exactly what I described. Like Bob wants to say, hello, Alice, and he encrypts it with Alice's public key. Okay, so Bob has Alice's public key, and he encrypts that message. Anyone can intercept that encrypted message, but they can't decrypt it because only Alice can, because only Alice has Alice's private key. Okay, so Alice has her private key and she can decrypt it. Okay, and so that's exactly what I described. Okay, if you want more information, I mean, this is pretty dense stuff, but this is more or less what you need to understand. Okay, now that's part of the story. The other part of the story was that you have to have these certificate authorities, and they issue what are called digital certificates. They just basically make sure that those public keys really belong to the people that they say they belong to. Okay, and like in the world of geeks, there's a lot of geek humor, and so there are public keys out there that belong to people like George Washington and or Albert Einstein. These are people obviously who lived a long time ago that did not have access to this technology, obviously, like George Washington. But people do this, and it's kind of, I guess, a geek joke. Okay, but no certificate authority is going to sign them. And so here's a list of some certificate authorities, and you go like there's IdenTrust and DigiCert, I know of, GoDaddy, that also does DNS. Okay, and Let's Encrypt is the one I use now. Okay, so there's a whole bunch there like that. Okay, last thing on this section, and that is what happens when your browser encounters a bad certificate? Or better yet, how do you even know your browser is doing encrypted communication? Okay, so I went to this site called badssl.com. It's basically a site which is meant to demonstrate exactly what happens when the public keys are broken in some way. And the first thing you need to note is I've got it highlighted there, but you can barely see it. Yeah, you can't see it. It's look at the URL up at the top there. Okay, and it says https https://badssl.com. The important thing to see is https. Now, you might see https there, or you might see http. Let me give you an example of http. If you go to http://www.dyc.edu, and you look at the URL there. Actually, it took out the HTTP and it just says not secure. Okay, so the browser I'm using is kind of a funny browser. It's called Dissenter, but it's the same in Firefox and other browsers. Basically, you can go to the website and can either be encrypted or not encrypted. And so if you just have HTTP without the S there, so just HTTP, or if it just says not secure like that, Duval College's webpage is not secure, what that means is that none of this information is encrypted. Okay, none of the information is encrypted. That's okay, it's just the front page, and it's not that bad that the front page isn't encrypted. Okay, so it's not like they're doing anything wrong, but basically, this web page is not encrypted, which means that the contents of those packets are not encrypted, and anyone can see anyone on the routers on the route from the destination to the source can see what you're doing. Okay, so like some intermediate router administrator can actually see that you're going to Duval's webpage. They can see what you're clicking on and so on. Okay, and you go, well, that's terrible. Well, maybe, but it's not that bad on the front page. Okay, but you can also go to this web page, and I think you can do this on Duval's webpage too. You can actually go with HTTPS, and that extra S there, HTTPS : that extra S, and yes, it did work. You can see there, it's very small, but it says HTTPS. That extra S means secure, and that secure part means that it's doing that public-private key encryption. Okay, and so everything is good. So when you go to your bank, your bank will automatically convert to HTTPS. Let's just pick a bank for whatever reason. We could just go to like KeyBank. So you could go www.key.com like that, and you could see that what happened there is it automatically switched to HTTPS. Okay, because banks are obviously going to be like, well, we're going to make you do encryption because obviously it's a bank. Okay, now back to this bad SSL site here like that. Not to tell you what SSL is, but it's just one way of creating these private public keys. Over here, there's like all different kinds of broken things that can happen with your key. Okay, and so one possible thing that can happen that's wrong is that it's what's called a self-signed certificate. That means that basically there is no certificate authority that actually signed it. It's just you're just pretending. Okay, so if you click on that, this is what your browser should do if you go to a site and it has a broken public key. Broken public key means for one reason or another, there's something wrong. Like it wasn't signed properly by a certificate authority. Someone's up to something nefarious, okay? And there's a lot of reasons. I don't want to go through all of them, but I do want you to see what it looks like in your web page because this is critical, okay? So most browsers now will not go to the site. They will go, the connection is not private or not secure or something like that. And up at the top, it'll say not secure there. And then in addition to that, it will show the HTTPS, but it'll show the HTTPS like with like maybe in red or with like a strike through or something that indicates that this is broken encryption. Here's the thing, it actually is doing encryption, but it's doing encryption with a compromised or bad public key, and so you shouldn't trust it. If you go to your bank and for whatever reason you get something that looks like this, just don't do banking. I mean, there are some situations, they're getting rarer as time goes on, but there are some situations where hackers have been able to redirect traffic in such a way as to, redirect bank traffic and then try to get into your bank account. And so if you see this, take it very seriously, okay? And there's a whole bunch of different things that can go wrong. That's one of them. That's the business of like self-signed, okay? Another one could be expired. Like these public keys, they don't live forever, okay? And this is kind of a funny message. It says your clock is ahead. Really, it's not that the clock is ahead. It's that the the certificate is expired. Okay, so that's kind of weird that it gave that message. But it basically says that the timestamp on the public key and the actual time that your computer has are out of sync. Okay, and so there's something wrong going there too. And again, for whatever reason, if you see that it's not secure, you need to just not go ahead. Okay, and like this has a lot of different reasons why it might be broken. Okay, so I don't want to go through all of them, but this site is basically used by web developers and other kind of like software engineers, they use this site to check their certificates. Okay, and so let's go back to where should we go? Let's go back to um, okay, we could look at DYC. So this is the DYC page, but it's encrypted HTTPS. Okay, and I'm going to show you who the certificate authority is, because if you click right up here where it says HTTPS, like there, it brings up, oh, it brings up that this site is not, oh, it's not fully secure. Okay, it's partially insecure. You know what? Let's do, again, that's a warning sign in itself. So it's only partially secure. Let's do key. Okay, and over here, we can click on that and you'll see that it says this site is secure. Let me see if, I'm not sure you're seeing that. Okay. I think you might be. Okay, I don't know if you're seeing that or not, but it's secure. And then there's you can click on that, and okay, that's showing up. This actually shows you the certificate. Okay, and these are the people that actually are verifying that this really is Key Bank. Okay, and if you go down and you take a look here under the details. Oh, here it is, right here. Common name issued by DigiCert. Okay, so DigiCert right here is the certificate authority that is saying yes, this really is Key Bank. Okay, all right, we're done with this. Last thing, a lot of this is done automatically in your browser, so you don't have to worry about it. You only have to worry about it if your browser is like screaming at you, like this kind of screaming. Okay, take it very seriously. Now you understand what's going on. Back in the day, it would do this and it would say, do you want to proceed? And a lot of people would just click okay, proceed anyhow, because they didn't understand the warning. No, take the warning very seriously. Okay, and in order for your browser to be doing this properly, it needs to be up to date. Okay, so most of this is automatic, but if for one reason or another your browser's out of date, you didn't update your browser, it might have some older certificate authority information in there which might have gone stale, it might be out of date, and then it might not catch some of these problems. Okay, so if there's anything to take away from this particular part of the security issue is one, make sure your browser is up to date, and number two, take it very seriously when you go to a site that's supposed to be secure. If you see HTTPS and for some reason it says not secure, it's got a cross through, every browser does it a little bit differently. Take that seriously. What's going on is you've got a broken public key. Okay, if the public key is not broken, like it is here with Key Bank, okay, and then you are certain that the communication between you and your bank is actually encrypted. Okay, it's encrypted, and it's encrypted with a known key. Back to the the bad SSL stuff. Wherever that is, I've lost it here. Oh, here it is. Yeah, the bad SSL stuff. It still says HTTPS. It is encrypted. But don't think that just because it's encrypted, that it's encrypted with a good public key. It might be encrypted with a bad public key, where bad means that for one reason or another, you can't trust it. Okay, so this is what that private public key does. That's a little bit different. It does encrypt it, but in addition to encrypting it, you have to make sure that you're encrypting it with a good verified key rather than a bad key. Okay. What does this take care of? Well, if we go back up here, remember these were the I guess 5 things, although number 5 is an open category. There are different things that can leak information. That is the most important one, the encryption of your contents. And if you can't even get that, the internet's kind of useless, except for just, I don't know, surfing pictures of puppies and kittens, right? Because you can't do business on it. Okay, but what about the rest of it? Can we actually use the internet in such a way as to hide your source IP address? Now, that's a little bit scary, it's a little bit deep, because how do you send a letter, thinking of snail mail, how do you send a letter and expect a letter to come back to you, but you don't put your return address on it? Okay, let me say that again. You could send a letter. You could put and put it in the mail. You just put the destination where it's going to, but you don't put the return address in there. You put the letter into the mail box, and it'll get to the destination. But nowhere in the letter do you put your return address. Nowhere. And you expect an answer. How are you going to get an answer back to you if you didn't say where the letter came from? Okay. Now, with letters, sometimes we just want to send the letter and we don't care about getting an answer back. Okay. Like I don't know, some third class mail or something like that. But sometimes we do want the answer back, or not sometimes, often we want the answer back. So that discloses who you are. That discloses your identity, because it says this letter came from so and so. And on the internet, it says this packet came from so and so. Is it possible for you to send a packet out on the internet and expect the packet to come back and actually reach you without disclosing to the destination what the source IP address? You say, well, why would you want to do that? That's anonymity. That's how you would be able to surf the internet anonymously and not have people know that it's you that are going to their site. Okay, you got to do a little bit more than that, because not only do you have to hide the source address, but you also have to hide the domain name, because remember, you're leaving those little breadcrumbs with the domain name servers. So you got to hide that, and you also have to hide the other stuff, okay, like these tracking cookies and things like that. Okay, because all of those things could disclose information. You say, is that possible? You might think it isn't, but it turns out that it is. Okay, I do want to, before I show you that, show how these tracking cookies work. Okay, so so we're heading towards like a full anonymity on the internet, and I think you understand the business of this business of source and destination IP addresses and content and DNS. But I think you need to understand just a little bit better how these cookies work. Okay, so let me go back to my browser here. Okay, and let me go to www.freeskies.net like that. Okay, and what you're looking at here is one of my servers, and this is a website on one of my servers, and it obviously is looking for a login. Okay, now you say, well, how do I log into this site? All right, and you put in a username here and admin, and you put in a password like this. Okay, and you click on it, and it logs you in. Okay, and oh, it didn't save that password. Okay, so we'll save that password. All right, and you're logged in. Now, when you're logged in, what you could do is you can browse the site. Okay, and then you can log out and so on. Okay, now take a look at that front page there. It actually says cookies must be enabled in your browser for this to work. And you say to yourself, well, why must cookies be enabled? And the reason that cookies need to be enabled in your browser is because if cookies were not enabled, after you log in, okay, like this, you would get to the first page, but then when you go to the second page, like, you click on, say, one of these, this is just like a site where I keep some of my information on courses, okay? And you click on the second page and you go there. Well, the computer needs to remember that you logged in, okay? And the way the computer remembers that you logged in, the way it did it, is it asks when you click on that page to go to that second page. Right here, we're clicking like on a third link. This is a third page within the same site. The server at the other end says, you remember that cookie that I gave you? All right, so it's the server that gives the cookie to the browser. Remember that cookie? Show it to me, because I want to know that it's really still you using this site. Okay, and so the way to think of a cookie is something like, when you go to a like a club, okay, like a concert or something, and you're allowed to go back out of the club and then go back in and go out. But when you come to the club and you pay like the cover fee to get into the club. Okay, I don't even know if people go clubbing anymore, but so you pay a fee to go in. They stamp your hand, okay? And then later you go outside, all right, because you want a breath of fresh air, and then later you want to come back in. But when you go back in, the bouncer's going to say, well, show me that stamp, because I want to make sure that you paid the cover fee. You show them stamp and they let you back in. You can go out and in like that, okay? That's exactly what was happening at that web page. When I first logged in, a cookie got put into my browser. Okay, and when that cookie got put into the browser, every time I go to another page in the same site, it's kind of like going out and then coming back into the club. It says, well, show me that cookie so that I know it's you. Show me that cookie that I know that it's you. Okay, and you show the cookie and then you can go to that other site. Well, the browser shows it for you. Okay, now, you know that in some sites, if you log in and then you wait like an hour or two, you don't get to go back in. It's kind of like they make you log in again. That's because these cookies go stale And what that means is that, your browser does show the cookie, but then the cookie says, 3 hours ago, and this browser and the server says, no, the cookie cannot be older than 1 hour, and it doesn't let you back in. Okay, that's a good cookie. That's a cookie that allows you to use the site over and over and over again. But people discovered that cookies could be bad. We can use them in a bad way. A site could put a cookie in your browser, and that cookie says something like, "This person is interested in lawnmowers." Why? Why did you get a cookie in your browser that says you're interested in lawnmowers? Well, that's because you might have been, shopping for lawnmowers. Okay, so you go to Amazon.com, I don't know, Home Depot, and you're like clicking on lawnmowers. True story, by the way. Looking for a new lawnmower, and what happens is a tracking cookie is placed into your browser, and this tracking cookie says this person is interested in lawnmowers. And then for like a month or two afterwards, you keep getting one after another ad about lawnmowers, and you go, well, how did they know that I was interested in lawnmowers? Well, you have this tracking cookie in your browser. Okay, and that's a bad cookie, because that's a cookie that's meant to, it compromises something of your privacy. Okay, it's looking for what kind of impulses you have. Okay, what kind of shopping impulses you have. All right, and so that's a bad cookie. Okay, so you had a good cookie, which is used for logins, but then that same technology can be abused. It can be used for as a bad cookie to track you between sites, and then basically the tracking is to track what kind of things you're shopping for. Now, I'm not going to show you how to do this because different browsers do it in different places, and I don't think it's that useful to show you in one particular browser. But if you go into the settings of your browser, just search for cookies, and there'll be a place that says clear all cookies, and you can actually see all the cookies that are in there, but you can clear all your cookies, and then your browser's been removed of those cookies. Okay, so this is kind of annoying, and to be honest, by themselves, even the tracking cookies, they're kind of bad, but they're not super bad. And some really bad cookies your browser's already made to look into, to stop. Okay, but if we go back to this, I mean, why did I take this break on the cookies? Because we want to hide our identity completely. So not only do we want to hide our source address, but we want to hide it's us. And if some server put a cookie in our browser that says, oh, this is the person that visited this site at such and such a time, they have your IP address, you've been compromised. Okay, so we have to also hide things like cookies, and then even more stuff that I don't want to get into, like JavaScript and so on. Okay, and you go, there's so much there. Is this possible? The answer is yes. It is possible to have nearly perfect anonymity online. Okay, basically hiding everything, hiding the source address, that's you. You can even hide the destination address from the intermediate routers. You know the destination IP because you're the person that's initiating it. But what about the intermediate routers? They could also see who you're communicating to. Is there a way to hide it from them? Yes. You have to hide the DNS because the DNS is, disclosing the IP address of who's going to what web pages. Okay, so you have to stop any kind of DNS requests from being logged. Okay, you have to stop the tracking cookies. Okay, and more. Okay, and you go, is this possible? Yeah. So another DARPA project that started in the early 2000s was a browser called Tor. Okay, and Tor is now available for your phone. I don't know if it's available for the iPhone. It is available for the Android because I had it on the Android, but I usually use Tor on my desktop and laptop. I don't usually use it on my phone. But you can get it from this site right here, https://www.torproject.org. Okay. Tor is kind of near and dear to my heart because I've actually done some development for Tor. I know the people that started it, and I haven't talked to them in a while. They might have forgotten about me, but I used to interact with them often. And we'll talk about open source later. But basically, I contributed some code to Tor. I helped make it better than it helped improve it. Okay, so what is this Tor, and what does it do for you? Okay, so basically, without getting into all of the details of how Tor works, okay, basically what it does is it creates these extra, like a layer on top of even the routers, okay, and these are basically known as Tor relays. And what these Tor relays do is they do the encryption, but they encrypt, they do an encryption within an encryption within an encryption. Okay, so let me describe how this works. Imagine a bunch of relays, Tor relays on the internet. Okay, so these are like routers, but they're at a higher level yet. okay? And what your browser does is it first negotiates with a bunch of Tor relays out there what route it's going to use, what bouncing through these Tor relays it's going to use. And it takes the innermost packet, the original packet, and it encrypts the whole thing, including the destination address. Okay, it encrypts it, and it encrypts it with one of the public keys of the last Tor router. And then it encrypts that within another layer for the second Tor relay, and then it encrypts that within a third layer for the what's called the entry node of the first Tor relay. And it sends the packet to the first Tor relay. Now, because it's been encrypted with the public key of the first Tor relay, anyone that intercepts it before it gets to the first Tor relay doesn't know what's in it. So remember, the deepest part of that packet, the encryption within the encryption within the encryption, the innermost piece, that's the part that has the source and destination IP address. That's been obliterated now. Because not obliterated, it's been encrypted, and so no one can see the destination. It gets to the first Tor relay, and the first Tor relay removes the first level of encryption and sends it to the second Tor relay. The second Tor relay doesn't even know it came from you because that information has been removed by the first Tor relay. Okay, I know this is a little complicated, but you remember these are like layers. This is like actually Tor stands for the onion routers. The onion routers, because it's layers on layers on layers. Okay, once it gets into that inner layer, the source IP address has been removed. It's again deep inside, and the first Tor relay doesn't tell the second Tor relay where it came from. So the second Tor relay gets this packet. It doesn't know where it came from. It doesn't know where it's going. It just knows the next Tor relay to send it to. It removes the second layer and sends it to the third Tor relay. The third Tor relay doesn't know about the first Tor relay. It only knows about the second one. And it removes that last layer and then finally sees the destination, okay, and it sends it to that destination. All right. By the way, I said it wrong. The innermost doesn't have the source. Okay, the outermost has the source. The innermost has the destination. So the third Tor relay has that destination in there, and it can send it to the destination. Okay, it comes back to the third Tor relay, and it knows that it came from the second, and the second knows that it came from the first, and the first knows that it came from you, and so it retraces its steps. Okay, so let me say that again. I did make one mistake. The innermost doesn't have the source. The innermost has only the destination. Then there's the next layer, which is for the third Tor relay. Then there's the next layer, which is the second. Then there's the first layer, which is for the first Tor relay. The first has the source, but not the destination. So it goes to the first, and the first knows it came from you. But once it removes that layer, it removes your IP address, okay? And it sends it to the second. The second doesn't know you, and it doesn't know the destination, because the destination's on the inside, and the first has been removed. It removes the second layer. It passes it to the third. The third knows that it came from the second, but it doesn't know any of the history before that. It removes that last layer and sees the destination, and it sends it to the destination. The destination then sends it back to the third, which sends it back to the second, which sends it back to the first. And in each sending it back, it again encrypts a layer so that only your browser, the last piece can see it. Okay. So, yeah, I'm not going to test you on this. It's a little bit heavy on the brain, but they figured out how to do this, okay? And if you want a metaphor, you could imagine that, if you're going to send a letter to someone, you don't send the letter directly to them. You send like a letter within a letter within a letter. The first letter goes to your first accomplice, who removes that outer envelope and hides your identity. That first person then sends it to their accomplice, which removes the second layer. They send it to the third accomplice, which removes the last layer and then sends it to the destination. And then on the way back, they re-encapsulate it within three layers the same way back. And remember, each Tor relay only knows the hop before and the hop after. It doesn't know the whole path. Okay, and because it doesn't know the whole path, the first one only knows you but doesn't know the destination. The second one knows neither you nor the destination, and the third one knows the destination but not you. Each one knows only the one immediately before and immediately after. So there's you, first Tor relay, second Tor relay, third Tor relay, and then final destination. Okay, so they figured out how to do it by layer upon layer upon layer. Okay, so Tor, the onion relay. Okay, originally it was a bit naive, but they got better, and they took care of the DNS. They have their own internal DNS, so there's a DNS system within Tor. Okay, and in addition to that, they simply tweak the browser so that they don't deal with they fake the cookies. Okay, so they actually lie back when a server asks for a cookie. They fake the cookies that come back. Okay, so there's no possibility of tracking through the cookies, and then other things like they turned off JavaScript, which means that some things don't work quite the same in a Tor browser than in a regular browser, but things do work. All right, so there's the Tor relay, okay, system. Okay, so you say, well, this is really cool. I want this. How do I get it? All right, so let me show you the web page to get that. It's this right here. So you go to https www.torproject.org. Okay, and you can click on right here where it says download the Tor browser. And it basically is Firefox, but it's Firefox done up such that it runs only through the Tor relay system. Okay, and there it is. This is there's the symbol right there, Tor, and you'll notice that the O is like an onion. Okay, all right. So I'm not going to download it and install it for you because I already did that. You start it up, and it takes a little longer than usual, but here we go. This is Tor. Okay, so you're looking at a browser, but it's a browser running through Tor. Okay, now you could just go to any old website like duckduckgo.com. Okay, and go ahead and um, just use that. So duckduckgo.com, if you don't know it, it's like another Google. Google does not like Tor, so Google tends to like reject the Tor servers, but DuckDuckGo uses it just fine. And let me show you. Let me show you this in. Let me show you Tor in practice. Okay, so if we go back to my server here. My server actually is running at a site called www.freekekistan.com. I know it's a silly name, but it's running there. And what it's doing there is it's actually running a web page, and that web page has its logs right here. Okay, so what you're looking at right now, all of that gobbledygook all over the screen, are basically the logs for everyone that visits my site. Okay, so I mean, I've got a few sites there that there was like Free Skies, but we're going to look at freekekistan.com. Okay, so if you're looking at this terminal here, what you're looking at is basically a log. All right, now what I'm going to do is in my regular browser, so I'm going to go back to this, which is my regular browser, and I'm going to go to the site Freekekistan, and let's see, where is that? There it is. Okay, Freekekistan. Okay, so you can see up here it says Freekekistan. Now the web page is kind of dumb. I just have like this word "re" there. Okay, it's just meant for demonstrations like this. Okay, and what I'm going to do is I'm just going to refresh the page. Okay, so I'm going to hit the refresh button. Okay, I'm going to hit it a couple of times, and let's switch back to my terminal. And what you could see is that 1, 2, 3, I guess I hit it 4 times. Okay, 4 times you will see a log entry for having gone to that web page. And you say, well, what's in this log entry? So every time you go to a web page, the server, that's the destination address that's running the web page, actually records that you visited it. Okay, what does it record? Well, the first thing it records is the web page that you went to right there, www.freekekistan.com. The second thing that it records is the IP address. Okay, so now you know my home IP address. Okay, and it records a whole bunch of other things. I don't record a lot. It could record more. Here's the time and date. Okay, it records, that like basically I was using Firefox and so on and so forth. Okay, but basically there's the IP address. That's the source IP address. And so what does that tell you? That identifies me. Okay, now what? Let's go to the Tor browser. So we're going to switch here to the Tor browser. I'm at the same site, but now what I'm going to do is, actually, let me go back here. I'm going to put a little bit of space in my logs there so you can see what's happening. Okay, and so now let me switch to the Tor browser, and now let me hit the refresh button. Now Tor is a little bit slower, so this might take a second, and you can see that it's trying, and hopefully this won't take too long. Oh boy. There it goes. Okay, so it finished. Let me do it again because it was establishing a route. Okay, and it does take a second. So the Tor browser is sometimes slow, but you're gaining this anonymity. And while this goes on, let's go back to the terminal here, and you could see over here that there are 2 new entries. Those are the 2 times that I hit the refresh button. And you could take a look. You could see it's www.freekekistan.com. But look at my IP address here and look at my IP address there. Okay? And you go, geez, that looks really different. That's right. Because that IP address that's highlighted is not my IP address. It's the IP address of that third Tor relay. Okay? That third Tor relay. By the way, as we were talking, this extra entry was someone, just coming by the site. In fact, it was the Bing bot. Okay? So there are these bots that go out on the internet and they basically just like look at web pages, and that's how you get indexing of web pages. Like Google does this, Microsoft Bing does that, and so on. Okay, but anyhow, let's just concentrate on these 2 IP addresses. This is the IP address through Tor, and it's not my IP address, and there's my IP address there. And you go, well, how can you use those IP addresses to find out who you are? So let's go back to the regular browser. Okay, and over here, I went to this site, and it's a good site to know. It's https://whatismyipaddress.com. Okay, all one word, whatismyipaddress.com. Okay, and if you go there, and I'm just going to hit refresh. It should come up pretty quickly. Okay, you go there and it's refreshed, and you'll see that it gives me my IP address. And there's a lot of information here. So first, there's my IP address, 172.114.17. And if you go back to the terminal there it is. Okay, so if I'm an administrator looking at the IP addresses as they're coming up in the logs, and I see this IP address 172.114.17, and then I can go to this site, what is my IP address, and it shows not only what the IP address is, but it also shows here, you can see on the map that it's in Buffalo. Okay, so they don't know who I am perfectly, but they certainly know my geographical location, and they can go further because they can call up my ISP and they could say something like, oh, the person that's doing this, who was visiting my site was doing something nefarious, etc., etc., etc. In other words, they put in an abuse claim and so on. So this is how they can track you down on the internet. Okay, now there was that other IP address, this one, and the same site can also be used to look up someone else's IP address. Okay, so if I take that IP address there, I'm going to copy and paste it. Okay, and let's go back to that site. All right, over here, and if we just go to the first page right there. Okay, we'll do it in. Sorry, the first page gives you my IP address, but up here I can actually do a search for a different IP address. I'm going to paste that IP address that I just cut and paste out of there. Now it's a little bit hard to see there, but there it is. It's 109.70.123. Okay, and now we can hit search, and we could see where that is. And this is kind of freaky. Okay, it says details for that IP address. It is in India, right there. Okay, so you can see the country, India, right there. Okay, and even there's the state and so on. And you go, what the heck just happened? Like, how in the world did my information get bounced around such that it appears that it's coming from India? So I don't know the first and second Tor relay, but my third Tor relay, also known as the exit relay, was right there. So as far as my server is concerned, that was in New Jersey. It sees the information, the traffic coming from India, not from Buffalo, New York. Okay, and so there you go. There's the magic of Tor. Okay, now that's kind of scary because you say, well, what can I do with this? I can do all sorts of nefarious things with this. You could, but like always, any technology can be used for good or bad. Okay, I've been telling you all through this lecture that you've got this problem where you're giving out all this information, and so people said, well, how do we fix that? And they came up with Tor. The same thing that allows you to do something bad, which would be something like nefarious, like some kind of hacking against the site, hiding your tracks, can also be used for good. You can use it for avoiding something like tracking cookies and things like that. Okay, now I didn't show you how Tor does the tracking cookies, and I didn't show you how Tor does the DNS, but there are similar things built into the Tor browser that prevents that. Okay, there's one more thing I'm going to show you about Tor, and then we can move on. And if we go back to the Tor browser here, okay, and we go to DuckDuckGo, that's my preferred search engine because they like privacy. We can ask for the Tor onion address for DuckDuckGo. Now, I don't know if this will come up, but if it does, what it'll show you is another way to get to Tor, to DuckDuckGo with Tor. Okay, and this may take a while, but where is it here? Oh, here it is. Here it is. Okay, so DuckDuckGo in your Tor browser. Okay, so what is this? There are ways to get to websites on the internet where it's the opposite of what we just did. What we just did is we hid the source, but we know the destination. What if you are someone that runs a web page and you want to run this web page on the internet, but you don't want anyone to know where that web page is, what server runs it? In other words, you want to hide the destination IP address. Well, there's a way of doing that too in Tor, and here it is. There are these addresses which are called onion addresses, and here it is right here. Now, they're kind of weird looking. Okay, so if you take a look at that, the one I have highlighted, it's got this weird name, and it starts off with like DuckDuckGo, and then it's got a whole bunch of letters and numbers there like that, and it ends in .onion. And you go, what the heck is that address? Like, what's that address? That is what's known as an onion address. It's running on a server. No one knows where that server is. In other words, you can't possibly know the IP address of the server, but if you use a Tor browser, you can actually get to that onion address. Okay? So if I click there, we'll see if it works. Again, this might be slow, so I may not wait too long because I don't want to waste your time. But basically, what's going to come up is, there it is, it's coming up. Basically, what's going to come up is DuckDuckGo. So you can see DuckDuckGo, the search engine. But take a look at the address in the URL up here. Take a look up there. You see blah, 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 .onion. Okay? If you cut and paste this in your regular browser will go, I don't know where that is. But if you go here to this .onion address, you'll basically go to DuckDuckGo. Okay? And that means that you know, the people that run DuckDuckGo, they're running it on some server and no one knows the IP address of that server so that no one can actually find the server. Okay? So that hides the server somewhere out on the internet, out in the Tor, on the Tor network. Now, if you're thinking you could do something evil with this, you're right, because you know you could buy and sell stuff through a web page, and you might say something like, now I don't endorse this, but just to be clear, you could say something like, what if I want to buy and sell drugs, or what if I want to buy and sell guns and things like that, or all these kinds of evil things? Could I do that through a web page that runs hidden on the Tor network? And the answer is yes, and believe it or not, someone did it. Okay, someone did it out of a server out of New York City, believe it or not. It was called the Silk Road, and for years, this person was buying and selling all sorts of stuff through this web page that was on the hidden network, and they were selling, you know, everything that's illegal. It was called the Silk Road. You can search Wikipedia for it. In fact, we could do that right now. Let's go to our Wikipedia page here, and we could just search for the Silk Road Tor network, like that. Okay, and the story should come up. There it is. Okay, there's the story. Okay, the Silk Road Marketplace, and you could see it looked like this, and it was an anonymous marketplace. It was online as a black market, and it was hidden on the Tor network. Okay, you can only get at it through the Tor network. Okay, and they were buying and selling stuff, and it took the police a long time before they caught them. Okay, and they eventually did. All right, so I think it was running. I don't want to read this right now, but I think it says here it launched in February 2011, and the FBI caught them in October 2013. Okay, and you might say, well, how did they exchange money anonymously? Well, there was a way of doing that through Bitcoins, which I'm going to tell you about in a minute. Okay, so there's the story with Tor. Okay, it's good to know more and more things are using Tor directly, like the Tor browser, but there's some people that are using Tor, they're actually making it part of their applications, okay, because it does give you this anonymity online. It's not just the security of encryption, it's encryption plus anonymity. which means that no one can see what you're doing on the internet, okay? And it's trying to hide as much as possible, okay? Again, be good netizens, okay? Be good citizens of the internet. Do this to hide yourself, okay? Or to go to some of these sites like these hidden sites, okay? Like DuckDuckGo is a perfectly legitimate site. You don't have to go to it through Tor. It's just an alternative search engine, but it's an alternative search engine which is also available on the Tor network, okay? And so you could go ahead and do that, and you'll then be safe and know that, when you go to a website, that website is logging the IP address, but it's not your IP address. It's the IP address of some Tor server somewhere like India, okay? Or, we do it again in a few minutes. It'll be somewhere else in the world. It'll be like somewhere in Europe or like in Russia or like whatever, okay? So there you go. We've come kind of full circle. We've come to the point where, we first had a completely insecure internet. And the first level of security was that asymmetric key encryption, the public-private key encryption, which allowed for the contents to be encrypted. And now with Tor, you're hiding pretty much everything, okay? It's not perfect, so don't think you can get away with everything. If you're using this and some like maybe you don't want Amazon.com to see what you're doing. Amazon.com is not going to be able to break Tor. But can the U.S. government do it? Could some, large country do it? Do they have enough resources to do that? Yeah, probably a large country could do that, okay? But there's a big difference between the resources that an entire country has and the resources that, say, like a company has. And so, if you just want to hide your tracks from a company so they don't see what you're doing on the internet, that Tor is a perfectly fine way of doing it. Okay, so what's next? Well, the last topic is not so much about security. Okay, I've kind of given you the full story about security. The last thing that I want to talk about is new technologies that the internet has made possible. Okay, and it's mostly this peer-to-peer business. Okay, but before we get to peer-to-peer, let me tell you about how the usual way in which files and services are shared on the internet. Okay, so this is kind of an old school way of doing it, but it's a perfectly good way of doing it. It's what's called the server-client model. Okay, now what is server client? What does that mean? Like, what are we even talking about here? Suppose that you want a file off the internet, and by a file I mean like maybe a web page. Okay, or you want a service off the internet. Okay, and a service could be something like registering for your courses. Okay, so when you go to register for your courses, you do that online through Duval's webpage. Okay, and so basically everyone goes to the same web page and gets the same service. There's one central computer which is responsible for that file or that service. It's called a server. And then there's all these clients, and the clients ask the server for the file, and the server serves them. Okay? It's kind of like a shopkeeper, if you want a metaphor. There's like one shopkeeper. Client comes in, and the shopkeeper serves the client, and they go out. And then another client comes in, and the shopkeeper serves them, and they go out, and so on. Okay? So one central shopkeeper, and so on. Okay? And this system works perfectly fine, except it's got some fallbacks. Okay? So if you're thinking like maybe a shoe store, okay, and someone comes in and asks the clerk there, the assistant, help me find some shoes. Well, while that server is helping you find the shoes, they're not available for the next client. Okay, and so if you just get one client at a time and you can serve that one client before the next client comes in, no problem, right? Because the server can take care of one client at a time, and so on. Okay, but suppose you have a really popular shoe. Okay, or on the internet you have a really popular file, something's gone viral, or you have a really popular service, like say the service for registering for a course at Duval College. It's popular because everyone wants to do it at the same time, like midnight of the night when it's available for your year. Okay, and so you're that one, again, to the shopkeeper, you're that one server sitting there, and like 20 customers come in at the same time. You're overwhelmed. You could take care of one, but these other clients are just sitting there waiting, and they give up. Okay, and I'm sure you've experienced this, where you go to a web page and it's not the internet, the speed of the internet that's a problem. It's not the routers that are a problem. It's that server themselves. The server themselves is overwhelmed. Okay, now like big sites like Google or Amazon, they hardly ever get overwhelmed, although they can be, but they hardly ever get overwhelmed. Okay, but like Duval's webpage, when everyone tries to register for the same course at the same time, it does get overwhelmed. Okay, and so this is a disadvantage because the system, the server client system, has a centralized point of failure, as it's called. And that centralized point of failure can fail for lots of reasons. One reason it can fail is because it's overwhelmed, like in my example. Another reason is that the computer just crashes. Okay, it just crashes, and that's like, like your shoe store salesperson kind of getting sick that day and not going into work. Okay, they get sick, and then all these customers come in, and there's no one to take care of them. Well, there you go. Okay, so you got a problem there. And so, like you got the centralized point of failure, and if it fails, that's it. The whole system is down. The computer could fail. The power could go out. Okay, like it only goes out in, say, the building where the server is at Duval College, and then no one can get to www.dyc.edu, and so it fails. Okay, now let's take a look at a picture for that. All right, so if we go here, we can go to the Wikipedia page here for client server, and basically this is kind of the picture you should have in your mind. You have like this one server, and you got a bunch of different clients. Okay, now the clients could be like anything. They could be like your laptop, they could be your phone, they could be your desktop, or whatever. Okay, basically the users are using the clients here, and they're making the request of the server. All right, and very easy to set up and very easy to understand how that works. Okay, now there's a bit of a description there, but kind of explains some of the difficulties. But here's the next thing we want to talk about. How does it compare to this other way of sharing out files, which is called peer-to-peer? So peer-to-peer, the way that works, here's the peer-to-peer web page. Okay, peer-to-peer, there is no centralized server. Every computer in the peer-to-peer network is a peer. They're like on equal footing. Okay, and you go, well, how does that work? How do these computers that are all on the same network, okay, they're all kind of like equal to one another, they're all peers, how do they share out files to one another? Okay, so this picture here is the server client model. Okay, you can see in the middle here. In the middle here is the server, and then all these clients, they form like a star. Okay, but the peer-to-peer is more like this. Okay, they're basically like every peer is kind of like on equal footing with the others. You say, well, how do they share out a file? Well, let me show you this picture down here. It's further down, further down, further down, further down. Here it is. Let's take a look at that picture. So what you're seeing right now is this one computer here. It is a peer, but it is the original peer called the seeder. It's the one that has the file. Okay. Now what it does is it does not share the file to any one of these, like the whole file to any one of them. Okay. Rather, what it does is it takes the file and it breaks it up into pieces. So what you're seeing here, this colored rainbow down here. Okay. So it goes from dark red to red, orange, yellow, green, and then a darker green. That's the file chopped up into pieces. And then what the server does is it sends one piece, like it sends the red piece to this peer, it sends the green piece to another peer. Then once this peer here has a red piece, it could start sharing it with that red piece with others. Even though this peer here doesn't have the full file, it can share out the pieces that it has with other peers. Okay, and so what winds up happening is at first all the pieces have to start coming out of the original seeder, and these other ones are called leechers, and here it's starting, so you can watch like a red piece goes there, but then the leechers can start to share with other leechers. Okay, and then once the leechers have the full file, they become new seeders. And so you can see here, this one got like some of the pieces from some of the other seeders, and now this one is another seeder, that's another seeder, that's another seeder. Now they all have the file. Okay, let's watch it one more time. We'll follow the red one. Okay, so seeder and the rest are leechers. Okay, so watch the red piece. It goes to here. Now this one has the red piece, so it can start sharing the red piece with that one. Now this one has the red piece and it got the green piece from another one. It can share the red piece with that one. Now this one has the red piece. And now this one doesn't even share the red piece, but it shares its orange piece with this one, and so on. Okay, so basically, rather than sharing the whole file at once, you share pieces of the file, and even if a peer does not have all the pieces of the file, they can at least start sharing parts of the pieces of the file. Okay, now with the server client model, the more popular the file is, the more clients there are, the more overwhelmed the server is. In this case, it's the exact opposite. The more peers there are, the more pieces get shared around, and the faster it actually starts to upload. Okay, so it's got the exact opposite scaling, as it's called, than the other one. With the server client, the more popular the service or file is, the worse it is, because clients start to overwhelm the server. In this one, the more popular the file is, the more seeders you get, and the more peers you get, and the more peers you get, the more sharing there is of pieces between the two, and then the file gets shared out more. And you can imagine, if all of these are seeders, okay, like right now they're all seeders now, almost. Okay, there they are. They all have all the full file. If another peer comes in, when a peer doesn't have anything, they call it a leecher. It can grab a piece simultaneously from all the other seeders, and it can download that file in no time at all. Okay, and so it scales the exact opposite to server client. Again, server client gets worse the more clients there are. Peer to peer, it gets better the more peers there are. Okay, and so that's good. So this is two different ways in which services and files can be shared on the internet. Okay, and this technology, this distributed technology, would not have been possible in the real world, because, well, I guess there are some distributed networks in the world, but the internet makes distributed networks very, very easy to implement. Okay, and so there it is. That's how basically peer-to-peer works. Okay, and again, just to remind you, there's one seeder, and initially there's one seeder. That's the computer that has the full file, and then there's a bunch of peers, which are called leechers because they don't have any part of the file. The seeder chops up the file into many pieces and just shares out, one piece to a few of the peers, and then the peers start to share amongst themselves, and that takes the load off of the original seeder, and eventually all the peers become seeders. And then if a new peer comes in as a leecher, it'll just leech off of all of them at once, and the file downloads extremely fast. Okay, now you got the idea of peer-to-peer. There's two technologies that I want to show you that are based on peer-to-peer technology. Okay, the first one is the easiest one to understand. It's BitTorrent. Okay, and with BitTorrent, it's basically a way of downloading a file. Okay, so how does BitTorrent work? Well, there's two parts to BitTorrent. First, you have to download what's called a torrent file. Okay, now you don't have to download it, because I'm going to show you how you can actually do this through your browser. But basically, the torrent file is not the file itself. It's simply a file that tells your computer how to join the peer-to-peer network. For every file that's being shared, it has its own peer network, okay, peer-to-peer network. So, like, I don't know, you want to share, like we're going to do the Ubuntu ISO. So you want to share the Ubuntu ISO, there's a network that's sharing the Ubuntu ISO. You want to share, say, a Gentoo ISO for another distribution, there's a peer that's sharing that, okay? This is used for piracy, okay? Because it's very hard to stop a peer-to-peer network. For a server client, it's very easy. You just take out the server and the whole system is gone, okay? But with a peer-to-peer network, it's very hard to stop it, because if you take out one of the peers, there's a whole bunch of other peers that are ready, to take over, okay? So especially once the file's been seeding for a while, there's lots of seeders. You could have hundreds of seeders. You take out one of the seeder because, the ISP calls you up and says, stop sharing that file that you're not supposed to be sharing. Great, you stop. You have to stop all 100 seeders before that file is gone. So these peer-to-peer networks, BitTorrent networks, are very robust. Okay, they're very hard to stop. Okay, they're not anonymous. So people could see that you're sharing the file. They can see your IP address on a BitTorrent network. Okay, so if you're sharing the latest movie, like the latest Disney movie or something like that, Disney's going to know that you did this. Okay, and people do get letters from these companies saying stop it. Okay, otherwise we'll sue you. They send these scary letters, but there's so many people doing it, I don't know how they'll stop everyone. But even if they stop you, are they going to stop people in Europe from sharing that file? They're going to stop people in in India, in China from sharing that file, because these peer-to-peer networks are global networks, and so it's very hard. They're very robust networks, and generally people are giving up. Companies are giving up on stopping this. Okay, unfortunately, that's just the way the technology's gone. That technology is just changing the business model. Okay, it has to. Okay, so there's this one file I was saying called a torrent file. It's not the file you want. It's the file that your browser or your BitTorrent client needs in order to get into the network. It has the information like, who do I talk to get into this network? Okay, and then once it gets into the network, then it starts sharing that file. Okay, now there's lots of BitTorrent clients out there. You could definitely get a BitTorrent client, and I like using them because they're specialized for BitTorrent. but most browsers today will do BitTorrent automatically. You don't even have to know that it's a peer-to-peer network. They'll just start doing the downloading automatically for you. Okay, so I'm going to demonstrate that for you because it's really easy now, and it's really robust, and it's a lot faster than downloading by server client. Okay, so here we are. Let's go back to our browser here, and let's go to Ubuntu. And I was already at the start off here at the main page. Okay, so you go to the main page of Ubuntu. All right, and I'm just picking on Ubuntu because I don't know, we saw it earlier, but there are lots of sites that do this, okay? And I don't want to go to a piracy site, but there's like the piratebay.com, which is a very popular piracy site, and you can download stuff using BitTorrent from there, okay? And you can see here where it says download. All right, so let's go to download, and you go to this page, and if you click on any one of these, which is what I did earlier when previous lecture when I got the Ubuntu ISO for the installation of Ubuntu in the virtual machine, this is purely server client. It's pretty fast, but there are other ways of downloading this, faster ways. And here we go. If you take a look down here, Ubuntu is available by BitTorrent. Okay, and so if we click on that, let's click on this link right here. It brings us to this page here, and so now it just says BitTorrent is a peer-to-peer network that sometimes enables higher download speeds. Okay, why higher download speeds? Because remember, there are lots of people that are seeding the ISO, and when you download, you're not just downloading from one other seeder. You're downloading from potentially hundreds of other seeders, and it can get so fast that it can actually like in your home, it could totally eat up your bandwidth, so that whoever else is trying to use the internet at the same time is going to find that the internet runs slow for them because you're eating up all the bandwidth. Okay, and let's go over here. Let's download the Ubuntu 2104 desktop 64-bit, and if we click on that, we get to this page. Now this page, you might wonder, what is this? Okay, this page is actually the page that says what do you want me to do with this torrent file? So you take a look at the name of the file, and there's the name of the file. Okay, look at it carefully. It ends in .torrent. This is not the file you want. This is not the ISO file, the final file you want. This is that intermediate file that tells your browser who's on the network. Okay, it allows your browser to get into that network, or your BitTorrent client. Okay, and the file that you actually want to download is this one. Okay, so torrent files, whoops. Okay, I did it again. Torrent files are basically the files that allow you to get into a BitTorrent network that is sharing the file that is previous to that .torrent extension. Okay, so we want the Ubuntu 2104 desktop AMD64.ISO. That's what we want. In order to get into the torrent network that is sharing that, we need the file called ubuntu-2104-desktop-amd64.iso.torrent. That file will tell our BitTorrent client or browser who's sharing that file, and then get into that network. There's two things we can do right now. We can save the file, which is this button right here, and that's if we want to use a different client to do this. But like I said, most browsers today can actually do BitTorrent. It's like BitTorrent is actually built right into the browser. So we're going to click on Start the Torrent, and you can see that it says downloading, and there it is. Okay, and if you take a look, this is a little slow, but it's saying how fast it's downloading and everything, and I'll read it out to you right now. It's downloading at 11 megabits per second, which my line can go faster. My line can go up to 100 megabits per second. Oh, that's megabytes. Okay, so multiply that by 8. So 88. Yeah, this is getting pretty close to saturating my line. Okay, it's got 90 peers. Now, not necessarily all of those peers are seeders, but it's like I'm downloading from 90 people at the same time. This file has been chopped up into a lot of little teeny pieces, and I'm downloading all those pieces at the same time, a lot of those pieces simultaneously, and there's about 87 people that I'm downloading from, and it'll be done in about 3 minutes. Okay, 3 minutes and 30 seconds. Okay, now I could let it continue, or I can stop the torrent, and I'm going to stop this torrent because I really don't want it. Okay, but I just showed you how that worked. Okay, now that torrent, that ISO was actually pretty big. Okay, and to have it download in 3 minutes means that basically it's like the size of a movie. I think it's like 3 gigabytes in size. Okay, basically almost like a DVD size. To have like an entire DVD download in 3 minutes is pretty fast. Okay, it basically is, like I said, totally saturating my line. All right, so there's a story with BitTorrent, and whoops, it is, um, you know, um, peer-to-peer, and it is robust, but it's not anonymous. Okay, and that means that if someone wanted to see, like it said, 90 peers there. And if you wanted to see the IP addresses of all those 90 peers, you can. Not in the browser, but all the other BitTorrent clients actually show you who the peers are. Okay, and if you see the IP addresses of the peer, you know who has that file. Okay, now like I said, for the Ubuntu ISO, no problem because they're giving it to you for free, and a lot of companies just give you their stuff for free via BitTorrent. But there are pirated stuff, and if there are these detectives that are hired by companies like Disney will actually hire an internet detective to see who's sharing their movies online. Well, they'll see your IP address. They won't catch you directly, but they know who your ISP is. They will write to your ISP, and your ISP will write to you and say, stop it, you downloaded this movie. Okay. In my entire lifetime, I got two DMCAs. That's what they're called, DMCA notices. They're like cease and desist notices, like stop doing this thing. One of them was, I used to run an IT lab at Juval College, and it wasn't me, it was one of my students that was doing it. They were downloading South Park season 13 many years ago. Okay. And I got a DMCA. And by the time I went to look who did it, they had stopped, and so that kind of was nowhere. And then I forget what the other one was. It was something I downloaded actually, but I didn't even know it was copyrighted, and then I got the DMCA. But I wouldn't freak out if you get a DMCA, but don't go pirating stuff. If you get enough of these, your ISP could terminate you. Okay, so there you go. There's a story with BitTorrent, but it is used for piracy. It's used for piracy precisely because it's robust, not because it's anonymous. But it's an excellent technology for sharing files and services on the internet. Okay, now BitTorrent is not so much about services, it's about files, and this brings us to our last technology, Bitcoins. So Bitcoins is a kind of new type of currency known as a cryptocurrency. Okay, now we could have an entire lecture, 3 hours or even more, on how cryptocurrency works, but it's not my purpose here to go through all the technical details. But Bitcoins is kind of like a distributed banking online. Okay, so banking, the way it works now, is kind of centralized. There's a central bank, and Bitcoins is kind of like all the computers that are part of the mining system form a kind of a distributed bank. Okay, and you say, well, what does that mean? First, the distributed is that it's peer-to-peer. And the second thing is that it's a bank. And you say, well, what is a bank? A bank is basically a record of transactions. Okay, that's really what it is. It's a ledger. Okay, so ledger is like a book where you write down all kinds of transactions. So if you go to the bank, now this is done with computers, but like in the old days, it was done in a book. You go to the bank and you deposit $100. Someone writes, deposited $100 into this account at such and such a date, and then they add that $100 to your account, and that's your total. Okay, now the equivalent of that is done by this distributed ledger, and the distributed ledger is shared. Transactions are shared between all the computers through a peer-to-peer network. Okay, now there has to be a way of making sure that you're not falsifying those records. Okay, and that's what's known as the blockchain, and I don't want to get into that because I think that's just a little bit too much for you, but you should know about this word blockchain because the blockchain is that distributed ledger that I'm talking about. Okay, so it basically has it's like this bank. Everyone that has Bitcoins is kind of like part of a bank. Okay, where everyone is like sharing information about who's trading Bitcoins with who, and that's how you have the totals of your Bitcoins. Okay, but that doesn't tell you what a Bitcoin is. So what is a Bitcoin? All right, well, it's actually this may sound strange, but it's actually the solution to a cryptographic puzzle. You say, what? Like a solution to a cryptographic puzzle? How is that money? How is that at all money? So we have to ask the question, what is money first before I can answer that? So money basically is something that we exchange. Okay, so I go to the to the store and I give them some money and they give me a loaf of bread. Okay, I give them some money, they give me some peanut butter. I give them some more money, they give me some jelly, and now I've got peanut butter and jelly sandwiches. I want the peanut butter and jelly sandwiches, and they want the money. Now, why do they want the money? Because then they can go off and exchange that money with something else. Okay, but if you take a look at a $10 bill or a $20 bill or a $50 bill, I mean, it's just paper and ink. It's hard to reproduce it. Okay, because you don't want people counterfeiting money, but it's just paper and ink. And if there's an apocalypse and our society falls apart, that $50 bill is worth no more than the heat that comes from it if you burn it, right? So you say, well, why do we have confidence in this $50 bill? In fact, there's just as much ink in a $50 bill as there is in a $1 bill. Same amount of paper, same amount of ink, but we value the $50 bill 50 times more than the $1 bill. In other words, if I go to the store and I buy something for $1 with this piece of paper, with a piece of paper that has the 50 on it, I can buy 50 of them. So it's valued at 50 times more. And you go, why is that? And some people will say it's because the government says that you're supposed to, but that's not it either, because there have been governments that have had currencies, and the currencies, people lose confidence in the currencies, and then the currency is worth nothing. Okay, they have hyperinflation, and the government says, no, believe in our currency, and the people go, no, we don't. We do not believe in your currency. And the reason they don't believe in the currency is because the government has issued too much currency. Okay, and people lose confidence in it, which is the scarcity that I'll get to in a minute. So the answer is, we simply believe that this currency has value and that we'll accept it for that reason. If the whole society wasn't just accepting $50 bills as $50 bills, then people started looking at this and going, I don't want that piece of paper, it's not worth anything, then $50 bills would be worth nothing. It's the confidence that we collectively have in the money that makes the money have value. Okay, and I know that sounds crazy, but really that's it. That is it. Okay, now money has to be scarce. You can't just do this with anything. Like, you can't do this with like leaves off of a tree. And you go, well, why not? Why can't we use leaves off of a tree as money? Well, because there's too much leaves. There's no scarcity, which means that people can, if they want more money, they just go pick more leaves. Now, imagine that you go to the store and you want to buy some bread. And you say, here, I'll give you 5 leaves for it. And the guy goes, why would I want 5 leaves? I can go pick 5 leaves if I want them off of my tree. And you go, well, I'll give you 10 leaves. And you go, well, no, I can get 10 leaves easily. And what about 50 leaves? No, my tree has thousands of leaves. I don't want your leaves. And that's no good for money. So when governments print too much money, in other words, they just make money. That's what they do. You're not allowed to make money. That's called counterfeiting, but the government can make money. And in the U.S., it's not really the government that makes it. It's the central bank, or the federal bank, sorry. And the Federal Reserve. So they make this money and they just give it to other banks that give it to other people, and it just becomes part of our circulation. If they make too much money, there's inflation. Okay, it's ironic that just last year in 2020 they printed 40% of all dollars that are in circulation. So we're going to see if we're going to hit a lot of inflation going forward or not. Okay, so I don't know. I mean, just a no. But if you give out money too easily, it inflates prices, and you could see that with houses. Imagine that banks just give out loans to anyone, and you want to buy a house and it's at $100,000. Well, I want that house at $100,000, but you also want that house at $100,000. You could go to the bank and say, I want 120. If the bank says yes, then that house is now worth 120 because you're going to bid 120. But if the bank is willing to go to it even more, then I can go to the bank and say, I'll give it 140. And then and then now that house is worth 140. But the bank is willing to give out 160 to someone, then it's worth 160. If the bank is willing to give out money like there's no tomorrow, then you can get into these bidding wars with houses, and the prices go up, 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 up. If there's no scarcity, if money is not hard to come by, then the problem is that it's not worth anything because money's easy to come by, and the prices will just go up and up and up and up and up. And if the money is infinitely easy to come by, then it's useless as money. And so money has to have scarcity. And guess what? Bitcoin has scarcity because these cryptographic puzzles, there's only 21 million possibilities. Basically, it's very difficult to solve these puzzles. You need huge computers to do this. I'm going to show you the computers that are used to do this. But you generate one of those, you solve one of those puzzles and you create 50 Bitcoins. Okay, you create 50 Bitcoins that way. And so they're very hard to generate, and that's what causes the scarcity. You can think of it as like gold. Why is gold precious? Because it's hard to find. And when there was the gold rush in the Yukon, people would go up there and it was still hard to find, and maybe they'd find a nugget, But whoever found that nugget would strike it rich because they found all this gold. Okay, and so it's scarcity is important. Okay, and again, you produce too much money, you're going to you generate too much money. The banks do, not you, because again, that's counterfeiting. You generate out too much money, you're going to inflate the prices by the process that I just described to you. Okay, so Bitcoins has a scarcity, and once upon a time, people thought, what the heck were these Bitcoins? It's kind of weird things. They're only for geeks. And nowadays, people have confidence in Bitcoins. And I think a Bitcoin's worth over $50,000 now. They were down like a couple of dollars each, but now they're at $50,000, believe it or not, for a Bitcoin. So yeah. People do have confidence in this, and they use them. Okay. Why were Bitcoins created? Okay. So that's why they're cryptocurrency, because they're not created by banks. They're created by by the solution to these cryptographic puzzles by these mining. They're actually called miners, by these mining computers. Okay, and that's how bitcoins are generated and injected into the field. So it's not, they're not under the control of any central bank. So why were these things created? That's precisely the reason. There were people that were angry at the central banks for controlling the money flow. Okay, and you go, well, these central banks, they can get rich by producing money, but you can't get rich from producing money. And so this was kind of a way, Bitcoins was kind of a way of like getting control back of the money system. Okay, now the guy who invented this, he's actually anonymous because he was afraid of the bankers, or you might call them banksters. Okay, because he knew what he was up to. He knew that he was creating a new kind of money that bankers could not have control over, and this was kind of a way of taking back the banking. His name, he goes by the name Satori, but we don't know who he really is. Okay, some people think they know who he is, but it's not clear. He wrote a paper and he used the pseudonym Satori, and I read the paper. It was brilliant. Okay, it was an excellent idea. He thought about everything. And this was like, I think in 2010, and here we are, 11 years later, and Bitcoins have really taken off. Okay, and there's other cryptocurrencies. Bitcoins was the first. I shouldn't say that that was it. Okay, so you got a bit of a background into this, and this was only possible because of that distributed ledger, and the distributed ledger was only possible because of peer-to-peer technology of the internet. You would not have had cryptocurrency the old way. You can only have cryptocurrency if you have computers and the internet. Amazing, isn't it? Totally new kind of money. Why? Because the money that's made by the banks is called fiat currency. Fiat means, it's the Latin word for let it be. Like fiat lux means let there be light. Okay, so fiat money. Okay, I guess in Latin that would be fiat pecunia. Let there be money. The banks just make this money out of nowhere, and they're allowed to do that. Okay, they're allowed to do. The government controls it, but the banks, they get rich from this. Okay, so banks create money out of nothing in the fiat currency system. That's what US dollars are. Whereas cryptocurrency is created by the random event at the solution of a cryptographic puzzle. Okay. All right. So, great. Now that you have this idea about Bitcoins, where do they come from? Like, how do they work? Well, first, you have to generate these Bitcoins, okay? And that's one way you can get Bitcoins is you can mine for them, okay? Now, most people don't do mining because it requires some really heavy-duty computing power to do that. In fact, now this will surprise you, you actually have to use super big graphics card. Remember those expensive graphic cards I showed you last lecture? It's those big graphics cards that they have like multiple parallel processing power. That's what you use to generate Bitcoins, to solve these cryptographic puzzles, okay? And so we can actually take a look at that. Let me see if I can, okay, there we go. Here's, let me get that up there. Here is a picture of a computer with multiple graphics cards that is being used for Bitcoin mining, okay? Now, what this mining is it just takes one of these available cryptographic puzzles, okay, and it just keeps trying to solve it. It's kind of like trying to crack a password where you have to try every possibility. And eventually, once you hit the possibility that unlocks it, you get a Bitcoin, okay? Now, this computer here, you say, well, where's the monitor and everything? There isn't a monitor. It's running what's called headless, that is without a monitor, keyboard, or anything, okay? And it's communicating through this wire here, which is an Ethernet wire, okay? And you could see that there's 1, 2, 3, 4, 5, 6 graphics cards on this computer, and those graphics cards are probably running at maximum, trying to crack a password. Okay, a password, like they're trying to crack the next block of the blockchain. Okay, and so that's one way, and that's just for like really hardcore geeks, okay? And I did some of that back in 2010. And I actually generated 3 Bitcoins, but I lost them because in those days, Bitcoins were worth nothing. If I kept those Bitcoins, each one would have been worth $50,000 today. But you know what? Everything is 2020 hindsight, okay? And I don't feel bad about it, but it's kind of cool that because I was teaching information technology to my students said, let's do a little bit of Bitcoin mining. And we said, sure, why not? So, using the computer, the college's computer equipment, we generated I think it was like 2 and a little bit, not quite 3, okay, but it was like 2 and a fraction of a Bitcoin, which today would have been worth like close to $150,000. But all water under the bridge. I don't know it's on some hard drive, and who knows where that hard drive is right now. Okay, story I like telling people. Here's another thing you can where Bitcoins are used. You can use them to buy and sell stuff. Okay, and so like there's some, like for instance Etsy. If you know Etsy.com, it's like just where people sell their crafts, but there's a lot of shops out there where they'll sell stuff using Bitcoins. Okay, now this was pretty popular some years ago, but it's not that popular today, and that is because this ledger has become so big that in order to transfer Bitcoins, it could take a long time. It could take like a day or even 2 days. Okay, and so you do a purchase with a credit card, and it happens instantly. You do a purchase with Bitcoins, and it's going to take a long time. So yeah, you could buy and sell Bitcoins, but people are not using Bitcoins that way today. Okay, they used to, but they're not. Today, they're kind of used like gold. They're kind of used as what's called a store value. So what people will do is they'll trade them like stocks. Like you buy and sell gold, you can buy and sell stocks. So people will will buy Bitcoins using US dollars, and they'll just keep it, these Bitcoins in what's called the Bitcoin wallet or online. Okay, although it's safer to keep it in a local wallet. And it just it goes up in price, it goes down in price, and so on. Okay, and you say, well, how do you do that? It's kind of like PayPal. Actually, PayPal allows you to buy Bitcoins. Okay, buy and sell Bitcoins. All right, it's kind of like PayPal. You connect your bank account to like an exchange, and then you can buy and sell Bitcoins that way. Okay, so let me show you an exchange, and let's see right here. Yeah, there we go. Okay, so this is an exchange. It's called CEX.io, and it's basically the buying and selling of Bitcoins. And let me refresh this page. I think the page just needs refreshing to see. Oh, here it is. Okay, there you go. Here's the price of Bitcoin. So this is like over, like this was at 8 o'clock this morning. You can see they went up, and then it kind of went up. It goes up and it goes down, and right now you can see at the side here a Bitcoin is selling for $57,000 and $57,027.10. Okay, so that's pretty good. Okay, considering that once upon a time, a Bitcoin was just a couple of dollars. Now Bitcoins have shot up to $57,000. Okay, now I'm not going to give any kind of financial advice. Let me just make that graph. You could see that. Oh, this is hard to navigate. Okay, I think this is good enough. This is going over like sometime. You can see that it goes up in price, it goes down in price, and so on. So, unless you know what you're doing, you could buy high and then you wind up selling low and then you lose money. And some people predict that Bitcoins will just die one day. They'll just like crash and go to $0. And so, it's hard to say what Bitcoins will do because it's so different. People don't know like the future of Bitcoins. So, I really don't want to speculate in the Bitcoin market. Okay. There are other kinds of coins too. Besides Bitcoins, Bitcoin was the first. It's by far the most popular. And it used to be kind of anonymous, but it's not really anonymous anymore. So there is another kind of coin called Monero. Monero is actually anonymous. And you say, well, why is anonymous good? Well, what if you want to buy and sell stuff and you don't want anyone to know who's paying for it? Okay. But you could still send the money to them and they can still know that it was you that sent the money, but they don't know who you are. Okay. And that's kind of like the Silk Road. All right. Again, I'm not endorsing any kind of illegal behavior, but when people used to buy stuff off the Silk Road, they used to use Bitcoins, but Bitcoins are not that anonymous. There are ways of like unraveling it. They used to think they were pretty anonymous, but they're not. So they're kind of like IP addresses. Like there's a number associated with them. You can unravel who that number is associated with. You figured out who's who that person is behind the bitcoins that were bought and sold. So they're not quite anonymous. But Monero was designed, it's kind of like another Bitcoin. It's not a cryptocurrency, but it was designed to actually be anonymous right from the get-go. So, like in the future, maybe people will want Monero instead of Bitcoins just for the anonymity, okay? And so, Bitcoins, they can be exchanged anonymously if done right, but most people don't. Monero is better for that because, like I said, Monero is actually like designed with anonymity in mind. Okay, there is no central bank which controls them, so people really like that. Okay, and it's for the reason I just said, because fiat currency can be inflated, whereas bitcoins really can't inflate. They're actually considered to be deflationary, which means that as time goes on, they'll expand in value rather than decrease. Okay, also, like no one can freeze your account with bitcoins. There's like a bank, like, don't get into a situation where you owe money and you're not paying it, because they can get a court order to freeze your bank accounts until you pay. Like a judge could say, no, you don't get the bank until you pay up. Okay, and so no one can freeze your bank account. All right, and then the last point is already what I said. No bank or government can actually print it, so no one really has control over the currency, and that's kind of a good thing, because you don't want a government to overprint money. And like I said, the U.S. government just printed an awful lot of money last year, and you can feel the inflation coming on. But there have been other countries that where the governments have gone crazy and they've printed so much money that their money is basically worthless. Okay, and then people stop trading in the money; they start trading in goods. Okay, basically black markets start to pop up, and these kinds of like other types of trades, because no one can trust the money. Imagine money that inflates at like 100% per month. Okay, so like your rent this month is $600. Your next month is going to be 100% more. It's going to be 1,200, and then rent the next month after that is going to be 2,400. It's just going crazy. Okay, the prices are going crazy. That's called hyperinflation, and yeah, governments can do that. Let's hope our government doesn't get stupid and do that. Okay, I don't think they will, but you never know. So people like bitcoins for that reason. Now, there's other things, like this is a changing world. Governments still have control, so they could say things like, when you go to exchange your bitcoins, we're going to tax that. Okay, we're going to want you to pay taxes on bitcoins, and they're going to make it harder and harder and harder for you to do things anonymously with bitcoins. And the more the bitcoins get regulated, the less they're going to have that original appeal that they had. Okay, but anyhow, bringing this lecture to a close, basically, you could see how this new technology of the internet, which started off as this insecure thing, had to be secured, and we created this encryption. And the encryption in turn allowed, with the internet and the kind of peer-to-peer stuff, allowed for this new type of currency to emerge out of like previous ideas that no one ever thought of before. So like when you first came up with the internet, they were just thinking about sharing data. But then people said, well, maybe we'll use it for business. But then to use it for business, you had to use encryption. But then, once you did the encryption, then you could have anonymity. But then once you had the anonymity, and, you had a very different type of an internet. Then, also with the encryption, you could have like peer-to-peer, and the peer-to-peer and the encryption together gives rise to cryptocurrency. Okay, so who knows what technologies will come next? If I had the foresight in 2010 to know that Bitcoins were where they are now, I would have retired a long time ago. Okay, so we don't know what the future will bring with this. Okay, so that's it for our lecture on the internet. All right, bye bye.